Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from? Perhaps you're wrapped in a blanket sitting by a softly lit window or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deep prehistory of our planet, to a time before oceans, before stone, before Earth itself had a name. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Far beyond the quiet orbit of present-day Earth, far before the sun settles into its steady middle age, a massive star approaches the end of its life. It does not rage, it simply runs out. In its core, hydrogen has long ago fused into helium, into carbon and oxygen, and then onward through heavier elements in layered shells, like the rings of a cosmic tree. Fusion proceeds until iron accumulates at the center, and iron, unlike lighter elements, does not release energy when fused. This is the accepted turning point in stellar evolution. Once iron dominates the core, outward pressure from fusion falters, and gravity, patient and exacting, takes over. The core collapses in less than a second. Electrons and protons press together into neutrons, releasing a flood of neutrinos that slip outward almost unhindered. The outer layers rebound in a supernova explosion, an event so luminous it can briefly outshine an entire galaxy. Only takes a few million years for a massive star to live and die. Only takes a fraction of a second for the collapse itself. Only takes gravity, which has been there all along. In that brief catastrophe, elements heavier than iron are forged through rapid neutron capture, a process known as the R process, creating gold, uranium, and other metals that will one day rest in planetary crusts and human hands. The expanding shell of gas carries these newly minted atoms outward into the surrounding interstellar medium. It is not dramatic in this retelling. It is simply matter rearranged under extreme conditions. A poetic detail lingers in the physics, some of the calcium in future bones. Some of the iodine in future oceans originates in these violent interiors, carried on shock fronts that travel for light years before thinning into cold space. The debris cloud does not remain a blazing remnant forever. It expands, cools, and mixes with nearby molecular clouds, composed mostly of hydrogen and helium, left from the Big Bang. Astronomers observe such remnants today as faint filamentary veils, supernova remnants, traced in radio and X-ray light, evidence that the cycle continues in other regions of the galaxy. The exact trigger that causes one small region of enriched gas to begin collapsing into a new solar system remains a quiet scientific uncertainty. Was it the shock wave from this very supernova compressing a nearby cloud? Was it a passing spiral arm density wave within the Milky Way? The evidence lies in isotopic ratios preserved in ancient meteorites, particularly short-lived radionuclides like aluminum-26, suggesting that fresh stellar debris was indeed present at the birth of the solar system. But the precise choreography remains partly veiled. The enriched cloud, now slightly denser in places, begins to contract under its own gravity. As it contracts, conservation of angular momentum causes it to spin faster, flattening into a rotating disk around a growing protostar at the center. This is a scientifically accepted process observed in young stellar objects across the galaxy, protoplanetary disks glowing faintly in infrared light, their dust lanes silhouetted against nebular backgrounds. Within this disk, microscopic grains of silicate and metal collide gently, at first sticking through electrostatic forces. Over time, these grains grow into pebbles, then into kilometer-scale planetesimals, through mechanisms that researchers still model with care. One lesser-known detail persists in laboratory experiments. Dust grains can acquire static charges that help them cling together in the earliest stages, like fine ash gathering in quiet air. Only takes a slight imbalance of charge. Only takes repeated collisions over thousands of orbits. Only takes patience measured in hundreds of thousands of years. The central protostar continues to accrete mass, its core temperature rising until hydrogen fusion ignites, marking the birth of the Sun. Around it, within the disk, heavier elements concentrate in the warmer inner regions, while lighter volatiles remain farther out. The gradient in temperature determines the architecture of the emerging planetary system: rocky bodies inside gas and ice giants beyond the frost line. There is no guiding hand here, only thermodynamics and gravity shaping probability into structure. A soft irony rests in the scale. The same heavy elements forged in the death of one star now gather to build smaller worlds around another. Only takes recycling on a galactic scale. Only takes one generation of stars to seed the next. Only takes time longer than any human lineage can imagine. As planetesimals collide and merge, some shatter, some grow, and some are flung outward entirely. The region that'll become Earth lies within a few astronomical units of the young Sun, where temperatures are high enough to prevent ices from condensing. The material here is metal-rich, silicate, heavy, dense. The early solar system is not serene. It is a field of intersecting paths, gravitational nudges, and frequent impacts. Yet even in this apparent chaos, motion follows precise equations described by Newtonian mechanics, later refined by general relativity. The orbits may shift, but they do so predictably. Astronomers today simulate these early epochs with computer models tracing how embryos of planets clear their neighborhoods and carve resonant gaps in the disk. Still, uncertainties remain about the exact timeline and number of collisions that assemble the proto-Earth. The evidence lies locked in isotopic signatures and the angular momentum of the present Earth-Moon system waiting for careful interpretation. In the vastness of interstellar space, the supernova that once seemed catastrophic has already faded into anonymity. Its remnants are diluted, its shock fronts dispersed. Yet its contribution persists in the composition of rocky bodies forming quietly around a modest yellow star. The iron that will one day sink to Earth's core begins as scattered atoms in a cooling nebula. The silicon that will form crustal rock drifts inward in dust spirals. The oxygen that will later bind with hydrogen to form oceans remains in silicate grains and gas. Nothing is wasted. Nothing is singular. The death of a star does not end a story. It redistributes ingredients. Only takes collapse. Only takes expansion. Only takes continuity written in atomic bonds. In this slow turning of matter, the stage is set for a planet not yet cooled, not yet named, but already carrying within it the memory of stellar fire. The enriched cloud does not hurry. Within the rotating disk around the young sun, dust and gas continue their quiet negotiation with gravity. The protostar now shines steadily, hydrogen fusing into helium in its core, through the proton-proton chain reaction, releasing energy that pushes outward against gravitational collapse. This balanced hydrostatic equilibrium is a stable arrangement, and it will persist for billions of years. Only takes 4 hydrogen nuclei and immense pressure. Only takes temperatures near 15 million degrees in the core. Only takes gravity holding everything inward while light presses outward. Around this stable center, the disk remains a broad, flattened plane of orbiting material extending for tens of astronomical units. Within it, particles collide thousands of times their velocities, shaped by turbulence and drag within the gaseous medium. The earliest stage of planet formation, known as hierarchical accretion, proceeds from micron-sized grains to pebble-sized aggregates. Laboratory studies suggest that at millimeter to centimeter scales, growth can stall due to fragmentation or rapid inward drift toward the sun, a difficulty known as the meter-size barrier. Yet models propose that local pressure bumps within the disk or streaming instabilities, caused by interactions between solids and gas, allow clumps to collapse gravitationally into larger bodies. The exact dominance of these mechanisms remains an open question in planetary science, inferred from simulations and the composition of primitive meteorites. A poetic detail lies in chondrules, tiny, once molten droplets found in ancient meteorites formed by brief heating events in the early solar system, perhaps from shock waves rippling through the disk. These millimeter-sized spheres carry within them isotopic clocks that measure time in the first few million years of formation. Only takes a flash of heat lasting hours. Only takes rapid cooling to preserve spherical form. Only takes billions of years for humans to notice them embedded in stone. As planetesimals grow to tens and then hundreds of kilometers in diameter, gravity becomes their dominant sculptor. Collisions shift from gentle sticking to energetic mergers. Some bodies fragment. Others coalesce into planetary embryos. In the inner solar system, these embryos interact gravitationally, their orbits crossing, leading to impacts that release extraordinary amounts of kinetic energy. The proto-Earth emerges from this environment, not as a finished sphere, but as a dynamic aggregate of merged bodies. Isotopic studies of hafnium and tungsten suggest that core formation occurs within the first 30 to 50 million years of solar system history, implying that differentiation begins early. Heavy elements such as iron and nickel sink toward the center of the growing planet, while lighter silicates rise. This separation is driven by density contrasts and by the immense heat generated from impacts and radioactive decay of short-lived isotopes like aluminum-26. The planet at this stage is not solid. It is at least partially molten, perhaps enveloped in a global magma ocean hundreds of kilometers deep. Only takes gravitational potential energy converted into heat. Only takes repeated collisions delivering fresh energy. Only takes radioactive decay releasing heat from within. The surface glows dull red beneath a thick atmosphere of vaporized rock and volatile gases. There are no oceans yet, No continents, only molten silicate currents moving slowly under the pull of gravity and rotation. The young sun, slightly dimmer than it will be in the future, shines through a haze of gas and dust. A lesser-known detail rests in the angular momentum budget of the forming system. Most of the mass resides in the sun, yet most of the angular momentum lies in the planets, especially the outer gas giants. This distribution remains an active area of research explained in part by early migration of Jupiter and Saturn within the disk. Their movements may influence the distribution of material in the inner solar system, shaping how much mass remains available to build Earth and its neighbors. Some models, such as the Grand Tack hypothesis, suggest that Jupiter moves inward toward the Sun before reversing direction, scattering material, and truncating the inner disk. Whether this migration occurs exactly as proposed remains debated, but evidence from asteroid compositions and orbital dynamics hints at early reshuffling. Meanwhile, the proto-Earth continues to grow. Each impact alters its spin, tilting its axis unpredictably. Its day length fluctuates as angular momentum is redistributed. The planet's gravitational field strengthens as mass accumulates, allowing it to retain heavier gases, while lighter hydrogen and helium escape into space. Outgassing from molten rock releases water vapor, carbon dioxide, nitrogen, and sulfur compounds, forming a thick primordial atmosphere. The composition of this early atmosphere is inferred from volcanic gas chemistry and from models of mantle degassing. Direct evidence has long since been erased by later processes. Only takes pressure building beneath solidifying crust. Only takes fractures venting steam into darkness. Only takes gravity strong enough to hold the heavier molecules close. Amid this environment, smaller planetesimals continue to strike. Some carry water bound within hydrated minerals. Others contribute additional metal to the core or silicate to the mantle. The cumulative effect is gradual assembly punctuated by episodic violence. Yet even violence is relative. On cosmic scales, these impacts are part of ordinary accretion. A gentle irony lingers the planet that will one day host forests and oceans forms through sustained collision. Only takes countless impacts. Only takes debris clearing its orbit. Only takes time measured in tens of millions of years. The inner solar system slowly transitions from a dense disk to a set of discrete bodies in relatively stable orbits. Mercury, Venus, Earth, and Mars differentiate along gradients of mass and composition. Beyond them, the gas giants complete their formation, sweeping up remaining gas and influencing the distribution of residual debris. The asteroid belt becomes a repository of leftover material, its growth stunted by Jupiter's gravitational influence. Meteorites that fall to Earth in the present era carry isotopic fingerprints from this ancient time, preserving records of processes that predate Earth's final assembly. The proto-Earth, now approaching its present mass, remains unstable and molten. Its core is largely formed, generating a magnetic field through convective motion of liquid iron, though the exact timing of dynamo initiation is still studied through paleomagnetic signatures in ancient zircon crystals. Some zircons dated to more than 4.3 billion years ago suggest that portions of Earth's crust may begin to solidify surprisingly early, perhaps even allowing transient bodies of liquid water to exist sooner than once believed. The interpretation of these crystals remains a subject of careful debate, but they hint at complexity emerging within what was once assumed to be a uniformly hellish world. The disk of dust that once encircled the sun thins its remnants, either incorporated into planets or expelled by radiation and solar wind. The environment grows less crowded, though not yet calm. One more event waits in the gravitational choreography, a collision that will reshape Earth permanently. For now, the planet spins beneath a dimmer sun, wrapped in steam and molten stone, carrying within it the heavy elements forged in a dead star gathered through patient accretion. Only takes gravity, only takes dust, only takes a nebula cooling slowly in the quiet after an explosion. The proto-Earth does not travel alone. In the inner solar system, several planetary embryos share similar orbits, their paths intersecting over millions of years in a slow gravitational negotiation. Among them is a body roughly the size of Mars, often referred to as Theia in modern models, though its true name, if it ever had one, is long dissolved into orbital equations. Computer simulations of late-stage accretion suggest that such collisions are not rare. They are expected outcomes when multiple large bodies compete within overlapping gravitational zones. Only takes slightly misaligned orbits. Only takes time for resonances to build. Only takes gravity to draw two worlds together. The impact when it occurs is neither cinematic nor abrupt in the way human imagination might prefer. It is the culmination of trajectories calculated across millions of revolutions around the sun. Theia approaches at a glancing angle, perhaps at velocities near escape speed, striking the proto-Earth with energy sufficient to melt large portions of both bodies. The kinetic energy released exceeds anything later known in planetary history, vaporizing rock and ejecting enormous quantities of silicate material into orbit. This is the widely accepted giant impact hypothesis for the Moon's formation, supported by isotopic similarities between lunar rocks and Earth's mantle. Lunar samples returned by the Apollo missions reveal oxygen isotope ratios nearly identical to Earth's, suggesting a shared origin. The precise mechanics of mixing between Theia and proto-Earth remain an active area of research. Some models indicate that the impact thoroughly homogenizes material, while others propose more selective incorporation. A quiet uncertainty persists in the exact mass and velocity parameters required to reproduce the present Earth-Moon system. The debris ejected into orbit forms a dense incandescent disk around the wounded Earth. Within this disk, silicate vapor condenses into droplets and fragments, gradually coalescing under self-gravity. Over the course of perhaps months to years, a remarkably brief interval compared to earlier accretion, the Moon assembles from this ring of molten and partially vaporized rock. Only takes orbital stability within the Roche limit. Only takes gravitational clumping beyond it. Only takes cooling and time measured not in eons but in seasons. The newborn Moon orbits much closer to Earth than it does today, perhaps only a few tens of thousands of kilometers away. Its presence profoundly alters Earth's rotation. The impact itself likely shortens Earth's day to perhaps 5 or 6 hours, spinning the planet more rapidly than at present. Tidal forces between Earth and the Moon begin an exchange of angular momentum that continues even now. Over billions of years, Tidal friction transfers rotational energy from Earth to the Moon's orbit, gradually lengthening the day and pushing the Moon farther away at a measurable rate of about 3.8 centimeters per year. This slow recession is recorded in the layering of ancient tidal sediments, subtle geological rhythms, preserving the memory of a closer Moon. A poetic detail rests in those layers. Ancient stromatolites and tidal flats encode shorter days and more frequent tides in their growth bands, silent witnesses to orbital evolution. Only takes friction between ocean and seafloor. Only takes gravity pulling unevenly on a spinning sphere. Only takes patience measured in billions of years. The immediate aftermath of the impact leaves Earth enveloped in a global magma ocean, once more perhaps deeper and more extensive than before. The energy released remelts much of the mantle, resetting thermal gradients. Volatile compounds, water, carbon dioxide, nitrogen, may be partially lost to space, while others remain trapped or reaccreted from debris. The question of how much water survives this event remains debated. Some models suggest significant loss requiring later delivery by volatile-rich asteroids or comets. Others indicate that substantial water could remain dissolved within molten rock and later outgas as the planet cools. The isotopic composition of hydrogen in Earth's oceans, particularly the deuterium to hydrogen ratio, provides clues linking much of Earth's water to carbonaceous chondrite asteroids rather than distant comets. Yet the balance between retained and delivered volatiles is not fully resolved. As the magma ocean gradually radiates heat into space, a crust begins to form. This first crust is unstable and thin, frequently overturned by convection currents beneath. Heavy elements have largely segregated into the core, by now establishing a layered structure: metallic core, silicate mantle, nascent crust. The core's rotation and convective motion generate a magnetic field, shielding the surface from charged particles streaming from the young sun. The timing of stable dynamo action remains under investigation, but paleomagnetic evidence from ancient zircons suggests that a magnetic field may exist as early as 4.2 billion years ago. Such protection would be crucial in preserving atmosphere and volatiles over deep time. Only takes molten iron moving within a rotating sphere. Only takes conductive fluid sustaining electric currents. Only takes rotation aligning field lines invisibly through space. The Moon, still close and luminous in the early sky, raises enormous tides in any molten or semi-molten surface material. Tidal heating may contribute additional energy to Earth's interior, though this effect diminishes as the Moon recedes. The gravitational partnership between Earth and Moon stabilizes Earth's axial tilt, preventing extreme variations that might otherwise arise from gravitational perturbations by other planets. This stabilization is subtle but significant, influencing long-term climate patterns. The extent to which the Moon is essential for climate stability remains a topic of modeling and debate. Yet its presence undeniably shapes Earth's rotational and tidal evolution. Meanwhile, the solar system continues to clear debris. Leftover planetesimals either collide with planets or are ejected by gravitational interactions with the gas giants. The environment remains hazardous, but the era of giant impacts gradually wanes. The proto-Earth, though still volatile and molten in regions, begins to transition toward a more stable configuration. Silicate minerals crystallize from cooling magma forming early basaltic crust. Zircon crystals, resilient and small, crystallize within these rocks and endure through later geological recycling, preserving chemical signatures of ancient surface conditions. Some zircons show evidence of interaction with liquid water astonishingly early in Earth's history, suggesting that cooling may proceed more rapidly than once assumed. Whether these signals represent global oceans or localized hydrothermal systems remains uncertain, but they hint that even after catastrophic collision conditions suitable for liquid water may emerge relatively quickly on geological timescales. Only takes radiative cooling under a dark sky. Only takes convection redistributing heat inward. Only takes a thin crust forming over molten depth. The moon's surface meanwhile cools and solidifies, preserving a record of early impacts that Earth later erases through tectonics and erosion. Its heavily cratered highlands stand as testimony to a violent epoch that Earth's dynamic surface will eventually obscure. Thus, the collision that might seem destructive becomes foundational. From it arises the moon, the stabilization of axial tilt, the modulation of tides, and perhaps conditions favorable for future oceans. The star that once died has already faded from memory, yet its elements now reside within a planet paired with a companion born of impact. Only takes one collision. Only takes gravity shaping debris into orbit. Only takes continuity from stellar death to planetary partnership. Beneath the cooling crust, heat still pulses, and above it steam begins to gather. The planet cools, though. Cooling on this scale is a relative word. Beneath a darkening sky, the magma ocean gradually loses heat by radiation into space, its surface intermittently crusting over, before being broken again by convective overturn. The young sun shines at perhaps 70% of its present luminosity, a scientifically established paradox known as the faint young sun problem, despite reduced solar output. Geological evidence suggests that liquid water will eventually persist on Earth's surface. The mechanisms that reconcile this paradox: higher concentrations of greenhouse gases, such as carbon dioxide and methane, are inferred from models and ancient mineral assemblages, yet their precise balance remains an open question. Only takes a thicker atmosphere trapping infrared radiation. Only takes volcanic outgassing replenishing carbon dioxide. Only takes time for feedback cycles to begin. As the mantle convects lighter, silicate minerals rise while denser materials sink, reinforcing internal stratification. The earliest crust, likely basaltic in composition, forms from partial melting of the upper mantle. It is thin and unstable, fractured by impacts, and pierced by volcanic vents that release steam and gases in continuous exhalations. These gases accumulate to form a dense primordial atmosphere, composed largely of water vapor, carbon dioxide, nitrogen, and trace sulfur compounds. Free oxygen is absent. It will not become significant for billions of years. The atmosphere at this stage may exert pressures far greater than present sea level, pressing downward upon a surface that still glows faintly from internal heat. A poetic detail lingers in the chemistry of volcanic plumes, microscopic droplets of silicate glass, quenched instantly in cooler air, drift and settle, becoming some of the earliest sediments. Only takes molten rock meeting cooler air. Only takes condensation in turbulent columns. Only takes gravity drawing ash back to ground. As surface temperatures decline below the critical point of water, condensation begins in earnest. Water vapor in the thick atmosphere forms clouds that darken the sky. Rain falls not in brief showers, but in prolonged, possibly millennia-long downpours, as the planet sheds its thermal excess. The first stable oceans accumulate in low-lying basins of the uneven crust. The exact timing of this transition is debated, but isotopic evidence from ancient zircons suggests that liquid water may exist as early as 4.3 to 4.4 billion years ago, remarkably soon after the moon-forming impact. These zircons contain oxygen isotope ratios that imply interaction with water at low temperatures, a subtle chemical whisper from deep time. Whether these waters form global oceans or localized bodies remains uncertain, yet their presence marks a profound transformation, the shift from molten world to hydrosphere. Only takes atmospheric cooling crossing a threshold. Only takes condensation exceeding evaporation. Only takes basins deep enough to hold accumulating rain. The oceans that gather are not yet blue in the modern sense. Dissolved iron from weathering crust gives them a greenish hue. Hydrothermal systems begin to operate where ocean water seeps into hot crust heats and rises again, enriched with dissolved minerals. These systems, still observed today along mid-ocean ridges, create steep chemical gradients differences in temperature, pH, and redox state that will later prove essential for life's chemistry. The circulation of seawater through newly formed crust facilitates chemical exchange between mantle and ocean, a process that continues across billions of years as plate tectonics evolves. Whether fully modern-style plate tectonics operates this early remains debated. Some geodynamic models propose a stagnant lid regime in which the lithosphere does not yet recycle in large moving plates, while others suggest that subduction-like processes begin surprisingly early. The geological record from the Hadean and early Archean is sparse, largely erased by later recycling, leaving this question partially unresolved. Meanwhile, the moon looms large in the sky, perhaps 10 times closer than today, raising tides far greater than modern equivalents. These tides churn shallow coastal regions, repeatedly wetting and drying newly formed shorelines. The rhythmic pull of the moon becomes a metronome for emerging cycles. Only takes gravitational asymmetry across a sphere. Only takes rotational inertia resisting that pull. Only takes friction dissipating energy into heat. The magnetic field generated by the liquid outer core continues to shield the surface from the young sun's stronger solar wind. Without such shielding, atmospheric erosion might proceed more rapidly, as appears to have happened on Mars, which loses much of its early atmosphere after its dynamo ceases. The comparison with Mars offers a quiet scientific analogy. Two rocky worlds form in similar epochs, yet differences in mass and internal heat retention lead to divergent histories. Only takes slightly smaller size. Only takes faster cooling of the core. Only takes magnetic silence for atmosphere to thin. On Earth, however, volcanism remains vigorous. Carbon dioxide released from the mantle dissolves in rainwater, forming weak carbonic acid that reacts with silicate rocks, initiating the long carbon-silicate cycle. Weathering draws carbon dioxide from the atmosphere and eventually deposits it as carbonate minerals on the ocean floor. This cycle operating slowly acts as a thermostat over geological time, regulating atmospheric carbon dioxide and surface temperature. The cycle's precise efficiency in the Hadean remains uncertain due to limited rock record, yet its fundamental chemistry is well understood. Only takes water interacting with silicate minerals. Only takes tectonic or volcanic recycling returning carbon to the atmosphere. Only takes millions of years for feedback to balance extremes. Impacts have not entirely ceased. The era known as the Late Heavy Bombardment, once thought to be a sharp spike around 3.9 billion years ago, is now debated. Some evidence suggests a more gradual decline of impacts, rather than a singular cataclysm. Lunar crater dating provides key insights as Earth's active geology erases comparable scars. The uncertainty illustrates the challenge of reconstructing early planetary history from incomplete archives. Still, impacts during this era may deliver additional water and organic molecules, though much of Earth's water likely originates from earlier accretion of volatile-rich asteroids. The oceans deepen as more water condenses and accumulates. Steam-dominated skies gradually thin, though carbon dioxide levels remain high compared to modern values. Lightning flashes through dense clouds, and ultraviolet radiation penetrates gaps interacting with atmospheric gases to drive complex photochemistry. Some scientists explore whether such photochemical reactions contribute to the formation of simple organic molecules, precursors to life. Yet the exact pathways from inorganic chemistry to self-replicating systems remain one of the most profound uncertainties in science. The ocean floor, warmed by residual heat and radioactive decay, hosts mineral-rich vents emitting hydrogen and methane, creating localized environments far from equilibrium. Only takes chemical gradients. Only takes catalytic mineral surfaces. Only takes molecules persisting long enough to interact. The planet now bears recognizable features: a metallic core generating magnetism, a silicate mantle convecting slowly, a crust fractured, and reforming oceans pooling in basins, an atmosphere thick and dynamic. From stellar debris to molten sphere to ocean-bearing world, the transformation proceeds without pause. There is no single dramatic turning point, only thresholds crossed quietly. The star that once died has given its iron to the core, its oxygen to water, its carbon to the air. Only takes redistribution. Only takes cooling beneath a dim sun. Only takes gravity holding everything close as rain falls on stone for the first time. The interval that follows is less spectacular in outward violence, yet more consequential in subtle chemistry. With oceans established and crust repeatedly formed and reworked, the planet enters the Archean eon, though that name will only be given billions of years later by beings who study stones and isotopes. The surface is darker than today, continents smaller. The sky tinted by gases unfamiliar to modern lungs. Nitrogen dominates the atmosphere. Carbon dioxide remains abundant, methane likely accumulates in measurable quantities, and oxygen persists only in trace amounts bound within water and rock. The sun, though still fainter than in the present era, brightens gradually as hydrogen fusion in its core increases luminosity over time, a well-understood consequence of stellar evolution. Only takes steady nuclear fusion compressing helium ash in the core. only takes incremental brightening across hundreds of millions of years, only takes planetary feedbacks adjusted to maintain liquid water. Shallow seas lap against volcanic island arcs and protocontinents, composed primarily of basalt and komatiite ultramafic lavas that erupt at temperatures hotter than most modern equivalents. Komateites preserved in some Archean terrains testify to a mantle hotter than today's by perhaps 150 to 200 degrees Celsius. Higher internal heat implies more vigorous convection, more rapid crustal recycling, and possibly different tectonic regimes. Whether plate tectonics as presently configured operates continuously through the Archean remains debated. Some models suggest episodic subduction, others a patchwork of short-lived plates. The geological record is fragmentary because subsequent metamorphism and recycling erase early structures. Only takes deeper burial transforming original textures. Only takes pressure and heat rewriting mineral assemblages. Only takes time to obscure first drafts of crust. Within oceans, chemistry evolves toward complexity. Dissolved iron from submarine volcanism accumulates in seawater under anoxic conditions. In the absence of free oxygen, ferrous iron remains soluble, imparting a greenish cast to the seas. Hydrothermal vents discharge hydrogen sulfide, methane, and metal ions into surrounding waters, establishing gradients of energy that can be exploited by redox reactions. Modern analogs along mid-ocean ridges and alkaline vents provide clues to plausible early environments. In such settings, microporous mineral structures composed of iron sulfides or carbonates can act as natural electrochemical reactors, concentrating molecules and facilitating reactions. Laboratory experiments demonstrate that simple organic compounds, amino acids, nucleobases, lipids, can arise under certain prebiotic conditions, though no single pathway is universally accepted as definitive. The origin of life remains an open scientific frontier, constrained by geochemical plausibility, yet lacking a complete narrative. Only takes carbon-forming versatile covalent bonds. Only takes energy gradients maintaining disequilibrium. Only takes membranes forming to separate inside from outside. At some uncertain point, before 3.5 billion years ago, life establishes itself. Evidence from isotopic signatures in ancient carbon, as well as stromatolite-like sedimentary structures, suggests biological activity by that time. The earliest organisms are microbial lacking nuclei thriving in anoxic environments. They metabolize using chemical pathways that do not require oxygen, such as fermentation, methanogenesis, or anoxygenic photosynthesis. These metabolisms likely evolve incrementally from pre-existing geochemical reactions. The boundary between chemistry and biology may be less abrupt than once imagined. Only takes self-replicating polymers subject to variation. Only takes selection favoring stability and efficiency. Only takes countless generations compressing chemical possibility into biological form. Among these early microbes, a transformative innovation eventually appears: oxygenic photosynthesis, performed by ancestors of modern cyanobacteria. Using sunlight to split water molecules, these organisms release oxygen as a byproduct. The reaction is energetically demanding and requires sophisticated molecular machinery, including photosystems capable of harnessing photons to drive electron transport chains. The exact evolutionary steps leading to this capability remain uncertain, but molecular phylogenetics suggests it arises well before the dramatic atmospheric consequences become evident. Initially released, oxygen does not accumulate in the atmosphere. It reacts readily with dissolved iron in the oceans, oxidizing ferrous iron to ferric iron, which precipitates as iron oxides. These precipitates settle to the seafloor, forming banded iron formations, layered sedimentary rocks, that serve as geological records of fluctuating oxygen levels. Only takes oxygen encountering reduced iron. Only takes insoluble oxides settling from solution. Only takes repetition over millions of years to build vast deposits. For hundreds of millions of years, oxygen sinks buffer atmospheric change. Volcanic gases and reduced minerals consume free oxygen almost as quickly as it is produced. Yet biological productivity gradually increases, and the capacity of sinks becomes saturated. Around 2.4 billion years ago, during what geologists term the Great Oxidation Event, atmospheric oxygen levels rise measurably. The transition is not instantaneous, but occurs over extended intervals with fluctuations. Methane, previously abundant, reacts with oxygen to form carbon dioxide and water-reducing greenhouse warming. Some models link this atmospheric transformation to global glaciations in the Paleoproterozoic, though causal relationships are complex and still debated. Only takes a shift in dominant metabolism. Only takes cumulative imbalance between sources and sinks. Only takes atmospheric chemistry crossing a tipping point. The consequences are profound. Oxygen is toxic to many anaerobic organisms, leading to ecological displacement or extinction in some lineages, while others adapt by evolving antioxidant defenses. At the same time, oxygen enables more efficient energy extraction through aerobic respiration, permitting greater metabolic complexity. The formation of an ozone layer in the upper atmosphere derived from molecular oxygen begins to shield the surface from harmful ultraviolet radiation, altering the photochemical environment. The sky, once hazy with methane, may gradually clear, shifting in color as atmospheric composition changes. Continents grow larger through accretion and magmatic differentiation. Granitic crust becomes more prevalent, buoyant relative to basaltic oceanic crust, allowing stable cratons to persist. The assembly and breakup of early supercontinents, names such as Kenorland and later Columbia, are applied by geologists illustrate cyclic tectonic behavior that continues through deep time. Supercontinent cycles influence ocean circulation, climate, and nutrient distribution, though precise reconstructions of early configurations are limited by sparse data. Only takes convergent plates thickening crust. Only takes rifting, splitting landmasses apart. Only takes mantle convection reorganizing surface geography. Climate oscillates across extremes. Geological evidence indicates episodes of widespread glaciation, even at low latitudes, suggesting snowball Earth conditions in later Proterozoic intervals, though earlier glaciations may also occur. The mechanisms behind global-scale freezing involve complex feedbacks among solar luminosity, greenhouse gases, continental arrangement, and biological activity. Once ice extends sufficiently toward the equator, increased reflectivity amplifies cooling. Recovery likely requires volcanic outgassing, accumulating carbon dioxide beneath ice-covered oceans, until greenhouse warming overcomes albedo effects. only takes reflective ice expanding surface brightness, only takes volcanic persistence beneath frozen skies, only takes greenhouse accumulation reaching critical thresholds. Through all these transformations, Earth remains governed by conservation laws, mass redistributed, but not lost to space in significant quantity energy flowing from sun to surface to infrared radiation emitted outward. The interplay between internal heat from radioactive decay and external energy from solar radiation shapes every epoch. Uranium, thorium, and potassium isotopes decay within the mantle and crust, providing a long-lived heat source that sustains tectonic and volcanic activity. Without this internal heat plate, tectonics might stall, limiting carbon cycling and long-term climate regulation. Only takes unstable isotopes shedding particles. Only takes heat diffusing upward. Only takes convection transporting thermal energy toward the surface. By the end of the Proterozoic multicellular life begins tentative experiments in organization, though that development lies beyond the immediate horizon of this section. For now, the planet has transitioned from molten chaos to chemically dynamic biosphere, from oxygen-poor atmosphere to one increasingly transformed by biology itself. The feedback between life and environment becomes reciprocal. Organisms alter atmospheric composition, which in turn influences evolutionary pathways. Earth is no longer merely shaped by physics and chemistry. It is co-shaped by biology. Yet the underlying processes remain continuous with earlier epochs. Only takes time extended across billions of years. Only takes incremental changes accumulating beyond intuitive scale. Only takes a planet retaining water tectonics and magnetic shielding long enough for complexity to emerge. The once incandescent sphere born of stellar debris now hosts oceans teeming with microbes, continents rising and eroding, skies slowly brightening beneath a strengthening sun. Nothing in this progression violates physical law. Everything follows from initial conditions and persistent feedbacks. The narrative from star death to living world is not a sequence of miracles, but a continuum of thresholds crossed. Only takes gravity gathering matter. Only takes fusion forging elements. Only takes cooling, cycling, and chemistry continuing without interruption. And in that continuity, complexity unfolds. The stage is set for visible complexity, though nothing about its arrival is abrupt when measured against geological time. Oxygen levels, having risen during the Great Oxidation Event, fluctuate for hundreds of millions of years before stabilizing at fractions of present atmospheric concentration. The oceans, once dominated by dissolved iron and anoxic chemistry, gradually transition toward more oxidized states. Nutrient cycles involving phosphorus, nitrogen, and trace metals intensify as continental weathering increases under oxygen-rich conditions. The interplay among tectonics, climate, and biology becomes more tightly coupled. Only takes continental uplift exposing fresh rock to weathering. Only takes rainfall transporting dissolved ions to seas. Only takes microbial metabolisms adapting to new chemical landscapes. Within this shifting environment, eukaryotic cells emerge. These cells, distinguished by internal compartmentalization and a nucleus enclosing genetic material, likely arise through endosymbiosis, one prokaryotic cell engulfing another that persists as a mutualistic partner. Mitochondria, the energy-producing organelles in modern eukaryotes retain their own DNA evidence of bacterial ancestry. This evolutionary innovation allows more efficient energy processing, supporting larger cell size and greater genomic complexity. The precise timing remains debated, but fossil and molecular evidence places early eukaryotes by at least 1.8 to 2.0 billion years ago. Only takes cellular membranes capable of engulfment. Only takes symbiotic persistence across generations. Only takes natural selection, preserving cooperative advantage. Multicellularity evolves multiple times independently in different lineages. Simple colonial organisms give way to differentiated tissues, where specialized cells perform distinct functions. Communication among cells via chemical signaling enables coordinated growth and development. Oxygen availability supports higher metabolic rates, making larger body plans feasible. Yet the path toward complex multicellular life is neither linear nor inevitable. It is contingent on environmental stability and genetic innovation. For long intervals, microbial life continues to dominate global biomass. Only takes incremental gene duplication, expanding regulatory networks. Only takes mutation introducing novel traits. Only takes ecological opportunity permitting diversification. During the Neoproterozoic era, Earth experiences dramatic climatic oscillations known as snowball Earth events. Geological deposits at low paleolatitudes indicate glacial conditions reaching near equatorial regions. Ice sheets may have extended across vast portions of the oceans, drastically altering albedo and suppressing photosynthesis. The triggers likely involve reductions in greenhouse gases, combined with continental configurations that enhance weathering. Recovery from these frozen intervals requires accumulation of volcanic carbon dioxide beneath ice-covered surfaces, until greenhouse warming initiates rapid deglaciation. The aftermath may include extreme greenhouse climates and enhanced nutrient delivery to oceans stimulating biological productivity. Only takes ice reflecting sunlight more efficiently than ocean water. Only takes volcanic outgassing persisting despite surface freeze. Only takes atmospheric carbon dioxide surpassing radiative thresholds. Following these oscillations, the Ediacaran period witnesses the appearance of macroscopic multicellular organisms preserved in sedimentary rocks. These soft-bodied forms, collectively termed the Ediacaran biota, display diverse morphologies, unlike most later animal lineages. Their ecological roles remain partially uncertain. Some may represent early animals, others evolutionary experiments that leave no direct descendants. Oxygen concentrations approach levels sufficient to sustain more active metabolisms. Ecological interactions grow more complex, including predation and burrowing behaviors that restructure marine sediments. Only takes developmental genes coordinating body axes. Only takes ecological competition driving innovation. Only takes oxygen diffusion supporting thicker tissues. Around 541 million years ago, the Cambrian explosion marks a relatively rapid diversification of animal body plans in the fossil record. Hard parts such as shells and exoskeletons appear enhancing preservation potential and providing defensive and structural advantages. The causes are multifactorial genetic toolkits involving Hox genes enable varied body architectures. Ecological arms races accelerate diversification. Environmental changes increase nutrient flux and oxygen availability. Though termed an explosion, the interval spans tens of millions of years, rapid geologically, but extended in human terms. Only takes genetic regulatory complexity reaching critical richness. Only takes predator-prey dynamics escalating selection pressures. Only takes sediment mixing altering nutrient cycling. Marine ecosystems diversify with arthropods, mollusks, chordates, and numerous extinct lineages. Photosynthetic organisms continue to shape atmospheric composition, maintaining oxygen levels within ranges compatible with complex respiration. Terrestrial surfaces, initially barren rock, gradually host microbial mats and later simple plants. The colonization of land requires adaptations to desiccation, ultraviolet radiation, and gravity. Vascular tissues evolve to transport water and nutrients, enabling plants to grow taller and influence atmospheric carbon dioxide through enhanced weathering. Soil formation accelerates linking biosphere and lithosphere more tightly. Only takes protective cuticles limiting water loss. Only takes supportive tissues resisting collapse. Only takes symbiotic fungi aiding nutrient uptake. Arthropods follow plants onto land, exploiting new niches. Vertebrates eventually transition from aquatic to terrestrial habitats during the Devonian period, modifying fins into limbs capable of bearing weight. Atmospheric oxygen fluctuates at times reaching higher concentrations than present, possibly supporting large arthropods due to diffusion-based respiration. Continental drift assembles supercontinents such as Pangaea, altering ocean circulation and climate patterns. Mountain-building events reshape weather systems and carbon cycling. Only takes tectonic plates converging across thousands of kilometers. Only takes erosion wearing mountains into sediment. Only takes burial of organic carbon reducing atmospheric carbon dioxide. Mass extinctions punctuate this history. The end Permian event approximately 252 million years ago eliminates a majority of marine and terrestrial species likely linked to massive volcanic eruptions in the Siberian traps, greenhouse warming, ocean acidification, and anoxia. The end Cretaceous extinction 66 million years ago follows an asteroid impact combined with volcanic activity, ending the reign of non-avian dinosaurs and reshaping ecosystems. These crises demonstrate that evolutionary trajectories are vulnerable to geophysical and extraterrestrial perturbations. Only takes rapid carbon release overwhelming climate regulation. Only takes impact energy injecting dust into the stratosphere. Only takes food webs collapsing when primary productivity falters. Mammals small and largely nocturnal during dinosaur dominance diversify after the Cretaceous extinction. Continental rearrangement continues forming the modern configuration. Climate oscillates between greenhouse and icehouse states influenced by orbital cycles, atmospheric composition, and ocean gateways. Grasslands expand, shaping herbivore evolution. Primates arise adapted for arboreal life. Among them, hominins evolve bipedal locomotion, increased brain size, and complex social structures. Only takes incremental neural expansion enhancing cognition. Only takes vocal tract modification enabling nuanced communication. Only takes cultural transmission amplifying learning across generations. Anatomically, modern humans appear in Africa roughly 300,000 years ago, according to fossil and genetic evidence. They develop symbolic language, art, and advanced tools. Agriculture emerges around 10,000 years ago in multiple regions, independently transforming landscapes through domestication of plants and animals. Urbanization follows, accompanied by metallurgy, written language, and technological innovation. Fossil fuel combustion in the industrial era releases carbon long sequestered in geological reservoirs, altering atmospheric composition at rates unprecedented in the recent geological record. Only takes stored solar energy accumulated over hundreds of millions of years. Only takes combustion reintroducing carbon dioxide to air. Only takes global connectivity accelerating technological diffusion. The Anthropocene, a proposed epoch reflecting significant human influence on Earth systems, is characterized by rapid climate change, biodiversity loss, and altered biogeochemical cycles. Atmospheric carbon dioxide concentrations exceed pre-industrial levels by large margins, intensifying greenhouse warming. Ocean acidification affects marine organisms that rely on carbonate shells. Land use change modifies albedo and hydrology. Yet the same species driving these changes possesses scientific understanding of planetary processes derived from disciplines spanning astrophysics to microbiology. Only takes reflective awareness of consequences. Only takes coordinated action modifying trajectories. Only takes recognition that planetary systems operate through feedback and threshold. From the condensation of a protoplanetary disk to the emergence of self-aware observers, the continuity remains unbroken. Physical law governs every transformations, gravity assembling mass thermodynamics, guiding energy flow, quantum processes, enabling chemistry. Biological evolution operates through variation and selection within environmental constraints, shaped by geology and climate. The sun continues its gradual brightening, ensuring that Earth's long-term future will involve further climatic shifts. Plate tectonics recycles crust, magnetic fields, shield atmosphere, and life modifies environment in recursive loops. Only takes time extended across billions of years. Only takes matter arranged under persistent forces. Only takes feedback cycles compounding subtle changes into profound outcomes. The narrative is neither predetermined nor random in the colloquial sense. It is structured by constraint and possibility. A molten sphere cools, oceans condense cells, replicate ecosystems, diversify intelligence reflects. The chain from stellar nucleosynthesis to conscious inquiry is continuous, each link contingent yet lawful. Only takes gravity holding a planet in orbit. Only takes sunlight bathing its surface. Only takes chemistry exploring configurations across deep time. And within that exploration, complexity arises capable of asking how it began. Reflection does not halt the processes it examines. The planet continues to evolve beneath the awareness of the species, now capable of modeling its past and projecting its future. The Sun, a main sequence star, gradually increasing in luminosity by roughly 10% every billion years, will not remain constant. Stellar physics indicates that as hydrogen in the core is fused into helium, the core contracts and heats, increasing the rate of fusion in surrounding shells. This incremental brightening ensures that Earth's long-term climate trajectory trends warmer even absent anthropogenic influence. Only takes core contraction raising temperature and pressure. Only takes higher fusion rates increasing radiant output. Only takes radiative balance shifting at the top of the atmosphere. In the nearer term, tens to hundreds of millions of years, plate tectonics will continue to reorganize continents. Models of supercontinent cycles suggest that the present configuration is temporary. Africa moves northward, Australia advances toward Southeast Asia, the Atlantic widens while the Pacific contracts. Given sufficient time, continents may assemble into a future supercontinent, sometimes referred to in speculative reconstructions as Amasia or Pangaea Proxima, though precise geometry remains uncertain. Only takes seafloor spreading at mid-ocean ridges. Only takes subduction zones recycling oceanic crust. Only takes mantle convection persisting as long as internal heat remains sufficient. Mountain ranges will rise where plates converge and erode under windwater and ice. Sediments will accumulate in basins, lithify, and potentially be uplifted again. The carbon silicate cycle will continue acting as a planetary thermostat, though its effectiveness diminishes as solar luminosity increases. Higher temperatures accelerate silicate weathering, drawing down atmospheric carbon dioxide, yet biological productivity depends on adequate carbon availability. Models suggest that within roughly 1 billion years, declining carbon dioxide concentrations, driven by intensified weathering under a brighter sun, may fall below levels required for C3 photosynthesis. Plant life, as currently structured, could struggle altering atmospheric oxygen and collapsing complex food webs long before oceans boil. Only takes enhanced weathering rates under warmer, wetter conditions. Only takes reduced volcanic outgassing relative to drawdown. Only takes photosynthetic thresholds crossed for ecosystems to falter. As luminosity continues to rise over billions of years, Earth may enter a moist greenhouse state. Increased surface temperatures enhance evaporation, raising atmospheric water vapor concentrations. Because water vapor is itself a greenhouse gas, this creates a positive feedback. At sufficiently high temperatures, water molecules in the upper atmosphere can be dissociated by ultraviolet radiation, allowing hydrogen to escape to space. Over extended intervals, this process can deplete oceans irreversibly. Planetary climate models differ in exact timing, but consensus suggests that a runaway greenhouse similar to that of Venus is a plausible far future outcome. Only takes saturation vapor pressure increasing with temperature. Only takes stratospheric water rising above cold traps. Only takes hydrogen atoms reaching escape velocity in the exosphere. Before such extremes, biospheric transformations will occur. Microbial life, particularly extremophiles tolerant of heat salinity or desiccation, may persist after complex, multicellular organisms decline. Subsurface habitats insulated from surface extremes could harbor life longer than exposed environments. The deep biosphere today already extends kilometers beneath the surface, sustained by chemical energy derived from rock-water interactions. Such niches might represent the final refuges of terrestrial life as surface conditions deteriorate. Only takes porous rock retaining water. Only takes radiolysis or serpentinization generating chemical gradients. Only takes cellular mechanisms enduring slow metabolism. Meanwhile, the Moon continues to recede from Earth at a rate of several centimeters per year due to tidal interactions transferring angular momentum. As it moves farther away, Earth's rotation gradually slows, lengthening the day. Tidal ranges will decrease over immense spans, subtly altering coastal dynamics. The stabilization effect of the Moon on Earth's axial tilt will persist, maintaining relative climatic stability compared to planets lacking large satellites. Yet over hundreds of millions of years, orbital resonances may still induce variations. Only takes tidal friction dissipating rotational energy as heat. Only takes angular momentum conserved within the Earth-Moon system. Only takes gravitational coupling across empty space. Eventually, approximately 5 billion years from now, stellar evolution will enter a dramatic phase. When hydrogen in the Sun's core is exhausted, the star will expand into a red giant. Its outer layers will swell outward, potentially engulfing the inner planets. Precise modeling of solar mass loss and orbital dynamics leaves some uncertainty as to whether Earth will be swallowed or merely scorched beyond habitability. But surface conditions will certainly become extreme long before physical engulfment. Oceans will have evaporated atmosphere stripped or transformed crust baked. Only takes shell hydrogen fusion surrounding an inert helium core. Only takes stellar radius expanding hundreds of times present size. Only takes radiative flux overwhelming any remaining planetary regulation. After the red giant phase, the Sun will shed its outer layers, forming a planetary nebula, while the core contracts into a white dwarf composed primarily of carbon and oxygen. This remnant will cool gradually over trillions of years, radiating residual heat into space. If Earth survives as a physical body, it will orbit a dim stellar ember, frozen and airless. Its geological activity long ceased as internal heat dissipates. Plate tectonics will halt once mantle convection can no longer overcome lithospheric strength. The magnetic field will fade as the core solidifies, completely eliminating dynamo action. Only takes radiogenic isotopes decaying below heat-producing thresholds. Only takes core crystallization inhibiting fluid motion. Only takes thermal gradients flattening until convection stalls. On cosmological scales, even this is not finality. Galactic dynamics continue as the Milky Way and Andromeda galaxies approach eventual merger in several billion years. Though by that epoch, Earth's habitability will already be lost. Stellar populations evolve. New stars form from recycled gas enriched by previous generations. Heavy elements forged in ancient supernovae persist in planetary bodies, white dwarfs, neutron stars. The matter composing Earth today originated in such stellar events billions of years before the Sun formed. Only takes gravitational collapse within molecular clouds. Only takes nucleosynthesis inside massive stars. Only takes supernova shock waves dispersing enriched material. From quarks bound in protons to atoms assembled in stars, from dust grains in protoplanetary disks to continents drifting across oceans, continuity spans scales of magnitude almost beyond comprehension. Entropy increases overall, yet local complexity arises wherever energy flows through matter under constraint. Earth's history exemplifies this principle. Solar energy driving atmospheric circulation, tectonic gradients, fostering chemical cycles, biological systems, harnessing disequilibrium to build ordered structures. Only takes sustained energy flux far from thermodynamic equilibrium. only takes mechanisms for capturing and storing free energy, only takes feedback loops reinforcing organized patterns. The observers tracing this arc mapping isotopic ratios, modeling stellar interiors, sequencing genomes, are themselves products of these processes. Cognitive capacity emerges from neural networks shaped by evolutionary pressures, which in turn are shaped by planetary conditions. Knowledge of deep time does not exempt humanity from planetary law. Rather, it situates human agency within it. Anthropogenic climate change demonstrates that even a single species can modify atmospheric composition rapidly when tapping concentrated energy reserves. Yet the same scientific understanding revealing vulnerability also offers potential for mitigation, adaptation, and stewardship. Only takes collective decision-making aligned with long-term systems thinking. Only takes technological innovation directed towards sustainable energy flows. Only takes recognition that planetary boundaries are finite. Whether human civilization persists for millennia or collapses within centuries remains contingent on social, ecological, and technological dynamics. Regardless of outcome, Earth's broader trajectory continues along astrophysical timelines indifferent to individual epochs. The lithosphere will recycle until heat wanes. The atmosphere will evolve under solar forcing, and ultimately stellar transformation will redefine the inner solar system. The chain from stellar birth to planetary differentiation, to biological evolution, to conscious reflection, remains unbroken by these future transitions. Only takes gravity shaping structure at every scale. Only takes thermodynamics constraining possibility. Only takes time measured not in years, but in billions for beginnings and endings to unfold. The narrative that began with collapsing interstellar gas culminates for now in a species capable of anticipating the red giant sun and the cooling white dwarf beyond. Yet anticipation does not alter the physics. It only deepens appreciation of continuity. A star ignites a planet, condenses oceans, gather cells, replicate minds, inquire. In that sequence, there is no abrupt discontinuity, only thresholds crossed under persistent law. Only takes matter and energy arranged by gravity. Only takes fusion forging elements and light. Only takes cooling worlds orbiting stable stars long enough for chemistry to become biology and biology to become awareness. And when awareness fades, as all localized structures eventually do, the underlying processes continue: stars forming galaxies, colliding entropy, increasing across expanses of time that dwarf even the longest planetary epoch. Beyond the red giant phase and the white dwarf remnant, the narrative widens from planetary destiny to cosmic duration. When the sun exhausts its nuclear fuel and settles as a cooling white dwarf, it will radiate residual thermal energy for trillions of years, gradually dimming from white to red to infrared invisibility. The timescale of white dwarf cooling vastly exceeds the entire prior history of Earth. Matter forged in stellar cores, carbon, oxygen, silicon, iron, remains locked within crystalline lattices of degenerate stellar remnants or dispersed into interstellar space. Only takes electron degeneracy pressure, halting gravitational collapse short of neutron star density. Only takes slow photon diffusion, releasing stored heat across unimaginable spans. Only takes the expansion of space stretching wavelengths ever longer. The Milky Way galaxy itself evolves. Star formation currently sustained by reservoirs of cold molecular gas will decline as gas is consumed or heated. The impending merger between the Milky Way and Andromeda, projected in roughly 4 to 5 billion years, will reshape galactic structure into a more massive elliptical system. Stellar collisions remain statistically unlikely due to vast interstellar distances, yet gravitational interactions will perturb orbits, possibly ejecting some stars into intergalactic space. By that epoch, the Sun will already have completed its red giant transformation, so Earth's fate is sealed, irrespective of galactic rearrangement. Only takes gravitational attraction operating across hundreds of thousands of light years. Only takes dynamical friction redistributing orbital energy. Only takes tidal forces reshaping spiral arms into diffuse halos. On still larger scales, cosmic expansion, first inferred from galactic redshifts and described mathematically by general relativity, continues to accelerate under the influence of dark energy. Galaxies beyond the local group recede ever more rapidly, eventually crossing a cosmological horizon beyond which their light can no longer reach observers in our region. In trillions of years, distant galaxies will fade from view, leaving future observers, if any persist, within gravitationally bound systems, with a sky largely devoid of evidence for cosmic expansion. The observable universe will contract in appearance even as space itself expands. Only takes metric expansion increasing proper distances. Only takes vacuum energy density remaining approximately constant. Only takes horizons limiting causal contact. Meanwhile, stellar evolution proceeds according to mass. Massive stars live briefly and die explosively as supernovae seeding surrounding space with heavy elements and sometimes leaving neutron stars or black holes. Lower mass stars, far more numerous, burn fuel slowly and will persist for trillions of years. Red dwarfs, the most common stellar type, may shine steadily for durations far exceeding the Sun's lifetime. Their longevity suggests that habitable environments could in principle endure around such stars long after Sun-like stars have vanished. Whether life arises or persists in those systems remains speculative, yet astrophysical conditions permit the possibility. Only takes proton-proton chains operating at modest core temperatures. Only takes convective mixing sustaining hydrogen supply. Only takes stable luminosity permitting temperate orbital zones. Over time, spans approaching 10 to the power of 14 to 10 to the power of 15 years. Star formation will effectively cease as interstellar gas is depleted. Existing stars will age into white dwarfs, neutron stars, or black holes. Galactic systems will dim, populated mainly by stellar remnants. Gravitational interactions will gradually eject many objects from galaxies through close encounters, a process known as dynamical relaxation. The universe will enter what cosmologists term the degenerate era, dominated by remnants and slow decay. Only takes cumulative gravitational perturbations over countless orbital periods. Only takes two-body interactions transferring kinetic energy. Only takes escape velocities exceeded through rare but inevitable encounters. On still longer timescales, proton decay, if it occurs as predicted by some grand unified theories, could transform ordinary matter itself. Experimental searches have yet to observe proton decay, placing lower bounds on its half-life exceeding 10 to the power of 34 years, so its existence remains unconfirmed. If protons are ultimately unstable, atomic nuclei will disintegrate, leaving a cosmos composed primarily of radiation, electrons, positrons, and neutrinos. If protons are stable matter, will persist in cold, dilute forms far longer. This uncertainty marks a boundary between established physics and theoretical extrapolation. Only takes rare quantum processes permitted by underlying symmetries. Only takes half-lives beyond observational reach. Only takes patience measured in exponents rather than centuries. Black holes formed from stellar collapse or residing in galactic centers as supermassive entities will dominate gravitational landscapes. Yet even black holes are not eternal. Quantum mechanical considerations articulated through Hawking radiation imply that black holes emit faint thermal radiation and gradually lose mass. The evaporation timescale for stellar mass black holes vastly exceeds current cosmic age. For supermassive black holes, it extends to around 10 to the power of 100 years or more. Nevertheless, given sufficient time, even these extreme objects dissipate into diffuse radiation. Only takes quantum field fluctuations near event horizons. Only takes particle-antiparticle pair production in curved spacetime. Only takes evaporation proceeding incrementally over inconceivable durations. As black holes vanish and stellar remnants decay or disperse, the universe trends toward thermodynamic equilibrium, a state of maximal entropy in which usable energy gradients disappear. Photons redshift to ever longer wavelengths. Temperatures approach absolute zero asymptotically, and interactions become rare. This projected heat death is not an explosive finale, but a gradual fading of structure and activity. Whether new physics alters this outcome through vacuum decay, cyclic cosmologies, or phenomena, yet unknown, remains speculative. Current observations favor continued accelerated expansion and long-term dilution. Only takes entropy increasing in closed systems. Only takes expansion reducing matter density. Only takes absence of free energy preventing complex organization. Against this cosmic backdrop, Earth's entire history, from accretion to biosphere to technological civilization, occupies a fleeting interval. The duration of multicellular life spans roughly 500 million years. Human technological society mere centuries. Yet within that brevity, matter organized itself into networks capable of reconstructing cosmic chronology and modeling epochs trillions of years ahead. This capacity does not suspend physical law. It exemplifies it. Neural computation arises from electrochemical gradients across membranes themselves, products of evolutionary adaptation within planetary environments shaped by astrophysical conditions. Only takes ion channels regulating membrane potentials. Only takes synaptic plasticity encoding memory. Only takes language transmitting abstraction across individuals. The same carbon atoms that circulate through Earth's biosphere were forged in ancient stars. The iron in hemoglobin traces to supernova nucleosynthesis, the calcium in bones to stellar cores. Stellar death precedes planetary birth. Planetary processes precede biological evolution. Biological evolution precedes reflective consciousness. Continuity threads through every scale. Only takes conservation of baryon number within known interactions. Only takes gravity assembling matter hierarchically. only takes quantum mechanics enabling chemical bonding. Even as the far future trends toward dilution and darkness, localized complexity may arise wherever energy gradients persist. Around red dwarfs, still burning, or near black holes accreting residual matter, transient structures could form. Yet the overall arc favors simplification over time. Structure requires gradients. Gradients dissipate. This asymmetry underlies cosmological evolution as surely as it underlies the cooling of a molten planet. Only takes second-law thermodynamics operating universally. Only takes time allowing probabilities to manifest. Only takes no external reservoir reversing total entropy growth. If the universe endures toward heat, death memory of early epochs will vanish with the observers that once contemplated them. Yet the processes themselves require no witness. Gravity will curve space-time regardless of awareness. Quantum fields will fluctuate in vacuum irrespective of observation. The narrative told across these sections, from stellar collapse to planetary cooling to biological emergence to cosmic fading, is descriptive, not prescriptive. It reflects patterns inferred from evidence and theory, bounded by uncertainty, yet constrained by tested law. Only takes equations validated by observation. Only takes spectra revealing elemental composition. Only takes background radiation mapping early density fluctuations. In the beginning of this account, a molecular cloud collapsed under gravity. In its midst, fusion ignited. Around it, dust coalesced into worlds. On one such world, oceans condensed and chemistry crossed into replication. Replication diversified into ecosystems. Ecosystems fostered cognition. Cognition traced origins to stardust. In the distant future, stars will dim and black holes evaporate, leaving a cosmos thin and cold. The chain is continuous, no abrupt creation, no sudden cessation, only transitions governed by invariant principles. Only takes mass and energy interacting across space-time. Only takes fundamental forces shaping structure from quarks to galaxies. Only takes duration extended beyond intuitive grasp. And within that immensity, the brief flourishing of life on a small rocky planet remains part of the same unfolding continuum, neither central nor negligible, but entirely consistent with the laws that bind atoms, ignite stars, and expand the universe itself. If the trajectory toward thermodynamic equilibrium defines the far future, the deeper question concerns origin, how the initial conditions themselves arose, and whether they represent a singular event or one phase within a larger, perhaps cyclical, cosmological structure. Current cosmology traces the observable universe to a hot, dense, early state approximately 13.8 billion years ago, inferred from cosmic microwave background radiation, galactic redshift, and primordial nucleosynthesis abundances. The expansion described by general relativity implies that space-time itself has been stretching since that early epoch. Yet the phrase beginning can mislead, for classical equations extrapolate toward a singularity, where density and curvature diverge, a regime in which known physics ceases to function predictively. Only takes mathematical solutions reaching limits of applicability. Only takes quantum effects becoming dominant at Planck scales. Only takes humility in acknowledging theoretical incompleteness. Inflationary cosmology proposes that a fraction of a second after the hot, dense state began exponential expansion, smoothed space-time and generated quantum fluctuations later amplified into galaxies. The evidence supporting inflation includes the observed flatness of space and the nearly scale-invariant spectrum of primordial density perturbations. Still, inflation's underlying mechanism, often modeled as a scalar field, with specific potential energy, remains unconfirmed experimentally. Competing models explore alternatives or refinements, yet none have displaced inflation as the leading explanatory framework. Only takes vacuum energy dominating early expansion. Only takes microscopic fluctuations stretched to cosmic size. Only takes gravitational instability amplifying slight overdensities. Before inflation or beneath it, speculation deepens. Quantum gravity theories attempt to reconcile general relativity with quantum mechanics, proposing frameworks such as loop quantum gravity or string theory. Some suggest that what appears as a singular origin may instead be a bounce from a prior contracting phase, or a transition within a multiverse where different regions possess distinct physical constants. These hypotheses remain beyond direct observational test. At present, though, indirect constraints may emerge through refined measurements of background radiation or gravitational waves. Only takes mathematical consistency across regimes. Only takes empirical signatures distinguishable from noise. Only takes patient accumulation of data refining parameter space. Regardless of ultimate cosmological origin, the early universe cooled sufficiently within minutes for light nuclei hydrogen, helium, trace lithium to form through primordial nucleosynthesis. Heavier elements required stellar interiors and supernovae linking cosmic chemical evolution to stellar life cycles. Galaxies condensed from dark matter halos, whose gravitational scaffolding guided baryonic matter into rotating disks and spheroidal structures. Dark matter itself inferred from gravitational effects on visible matter and cosmic background anisotropies remains unidentified at the particle level. Experiments seek weakly interacting massive particles, axions, or other candidates, yet confirmation remains elusive. Only takes gravitational lensing revealing unseen mass. Only takes rotation curves defying luminous matter distribution. Only takes careful statistical inference across cosmic surveys. Dark energy driving accelerated expansion presents an equally profound mystery. Whether it represents a cosmological constant intrinsic to spacetime or a dynamic field evolving over time remains uncertain. Observations of distant supernovae, baryon acoustic oscillations, and background radiation collectively support acceleration. Yet the physical origin of dark energy remains among the most significant open problems in physics. Only takes precise luminosity distance measurements. Only takes consistent deviation from decelerating models. Only takes theoretical frameworks broad enough to encompass unexpected parameters. From these early cosmic conditions arose the hierarchy of structure clusters, of galaxies, star systems, planets. Complexity emerges not in defiance of entropy, but locally sustained by gradients established during expansion and gravitational collapse. The same principle applies at every scale energy flows, permit temporary decreases in entropy within subsystems, while total entropy increases overall. Stars convert gravitational potential energy into thermal radiation. planets intercept a fraction, enabling atmospheric circulation and biochemical processes. Only takes non-equilibrium thermodynamics, allowing self-organization. Only takes open systems exchanging energy with surroundings. Only takes sufficient time for pattern stabilization. The possibility of life elsewhere arises naturally within this framework. Exoplanet surveys reveal that planets are common, many residing within habitable zones of their stars, where liquid water could persist. Atmospheric spectroscopy begins to probe chemical compositions, searching for biosignatures, such as oxygen-methane disequilibrium. Yet interpretation requires caution. Abiotic processes can mimic biological signals. The emergence of life on Earth occurred relatively early after planetary stabilization, suggesting that under suitable conditions, biogenesis may not be exceedingly improbable. Still, a single data point cannot establish frequency. Only takes statistical sampling across thousands of systems. Only takes refined detection methods reducing false positives. Only takes patience as instruments improve across decades. Intelligent life introduces additional contingencies. Technological civilizations may arise rarely or briefly constrained by ecological limits or self-induced collapse. The so-called Fermi paradox, why no clear evidence of extraterrestrial intelligence has been observed, admits numerous explanations: vast interstellar distances, transient technological phases, non-expansionist behavior, or simply insufficient search duration. The absence of evidence is not definitive evidence of absence, yet it shapes probabilistic reasoning. Only takes limited observational windows. Only takes civilizations separated by millions of years. Only takes communication methods misaligned across cultures and physics. If intelligence persists and expands, it might adapt to changing cosmic conditions. Advanced civilizations could, in theory, harness stellar energy on large scales, migrate between star systems, or exploit long-lived red dwarfs. Far future strategies might involve extracting energy from black holes or preserving information in durable substrates. These scenarios remain speculative yet consistent with known physics within constraints. Only takes engineering bounded by thermodynamic law. Only takes information storage resilient to radiation and decay. Only takes survival strategies aligned with cosmic timelines. Information itself becomes central in late cosmological considerations. As entropy increases and usable energy declines, maintaining structured information grows more costly. Theoretical discussions explore whether consciousness or computation could persist in a cooling universe by operating ever more slowly, stretching subjective time while expending diminishing energy. Yet even such adaptations face limits imposed by quantum fluctuations and finite resources. Only takes minimal energy per logical operation bounded by Landauer's principle. Only takes background temperature approaching absolute zero. Only takes diminishing gradients restricting computation. In contemplating origin and destiny, the narrative remains constrained by empirical evidence and theoretical coherence. Speculation must align with established physical law or clearly signal its hypothetical nature. The arc traced from cosmic expansion to planetary life to reflective awareness does not imply purpose in a teleological sense. It reflects causal continuity. Gravitational collapse yields stars. Stellar nucleosynthesis yields elements. Chemical complexity yields replicating systems. Evolutionary dynamics yield cognition. Only takes cause preceding effect within consistent frameworks. Only takes initial fluctuations amplified by deterministic and probabilistic laws. Only takes no violation of conservation principles. Whether the universe is singular or one of many, finite or infinite in extent, cyclic or asymptotically expanding, remains under investigation. What is established is that complexity can arise where energy flows through matter under constraint, and that such complexity can generate models of its own origin. The observer becomes a product of the process observed. Only takes atoms arranged in neural networks. Only takes symbolic abstraction encoding physical law. Only takes curiosity sustained across generations. Thus, the continuum extends from quantum fluctuations to galaxies, from galaxies to stars, from stars to planets, from planets to life, from life to minds capable of tracing this sequence. The future trends toward dilution and equilibrium, yet the present remains rich with gradients and structure. The laws governing both origin and destiny are uniform across space-time to the best of current measurement. Only takes invariance of physical constants across observable regions. Only takes symmetry principles shaping interactions. Only takes time enough for equations to unfold their implications. In that unfolding, beginnings are transitions from prior states, and endings are transitions toward others. The cosmos neither requires nor excludes awareness. It permits it under specific conditions. For a finite interval within an expanding universe, matter organizes into beings who ask how it all began and how it will end. The answer, as far as evidence allows, is continuous transformation under stable law. Only takes expansion from a hot, dense state. Only takes cooling enabling structure. Only takes gravity, thermodynamics, quantum mechanics, and time. And with those, the entire arc from first light to final fade remains one unbroken process. Continuity extended to its furthest logical boundary invites a final refinement, not merely how structures arise and dissolve within physical law, but how law itself is understood. The equations describing gravity, electromagnetism, nuclear forces, and quantum behavior appear invariant across observable spacetime. Measurements of distant galaxies show atomic spectra identical to those measured in laboratories, implying that fundamental constants within experimental limits have not drifted significantly over billions of years. This empirical uniformity underwrites every extrapolation from early universe to far future. Only takes spectral lines matching predicted transitions. Only takes fine structure constants remaining within narrow bounds. Only takes reproducibility across independent observations. Yet the question of why these constants possess their specific values remains open. Slight variations in gravitational strength, electromagnetic coupling, or nuclear binding energies could preclude stable stars or complex chemistry. Some physicists argue this apparent fine-tuning suggests deeper underlying principles not yet discovered. Others invoke selection effects within a multiverse framework, where many regions with varied constants exist, but observers arise only where conditions permit complexity. At present, both positions remain hypotheses constrained by theoretical plausibility and indirect inference rather than direct verification. Only takes parameter sensitivity analysis, revealing narrow life-permitting ranges. Only takes mathematical models permitting broader variation. Only takes acknowledgement that explanatory depth has limits pending further data. Scientific understanding proceeds through iterative refinement. Observations motivate theory. Theory predicts phenomena. New instruments test predictions. The cosmic microwave background, once a faint uniform glow, revealed anisotropies at parts per 100,000 precision when measured by successive satellites, sharpening constraints on cosmological parameters. Gravitational waves predicted a century before detection were observed, from merging black holes confirming general relativity under extreme conditions. Each confirmation extends confidence in extrapolations, yet each also opens new questions. Only takes interferometers measuring distortions smaller than atomic nuclei. Only takes cryogenic detectors isolating faint microwave fluctuations. Only takes collaboration across generations accumulating precision. The continuity described across prior sections, from stellar nucleosynthesis to planetary evolution to biological complexity, rests on this expanding evidentiary base. No stage requires suspension of physical law. Each emerges from interactions governed by equations tested within their domains. Where uncertainty persists, origin of life pathways, quantum gravity regimes, dark matter composition. It marks frontiers rather than gaps, inviting arbitrary insertion. Only takes disciplined skepticism, distinguishing known from conjectured. Only takes error bars reported alongside measurements. Only takes willingness to revise models when anomalies accumulate. In reflecting on the arc from cosmic origin to cosmic dilution, perspective shifts. Human temporal intuitions evolved within lifespans measured in decades. Geological and cosmological timescales exceed intuitive grasp by orders of magnitude. Exponential notation becomes necessary, not for rhetorical flourish, but for numerical accuracy. 1,000,000 years, 1,000,000,000 years, 1,000,000,000,000 years each differs by factors of 1,000. Only takes logarithmic scales representing proportional change. Only takes mathematical abstraction bridging cognitive limits. Only takes education transmitting these abstractions culturally. Within that abstraction lies practical implication. Planetary stewardship operates on decades to centuries horizons, yet its context includes tectonic cycles, solar brightening, and eventual stellar evolution. Recognition that Earth's habitability is finite on billion-year scales does not diminish urgency on century scales. Rather, it underscores rarity. Complex life has occupied only a fraction of Earth's history. Technological civilization, an infinitesimal slice, only takes comparative timeline visualization, only takes fossil records spanning stratigraphic columns, only takes orbital mechanics predicting stellar luminosity increase. The continuity of cause and effect also clarifies that no stage is isolated. Anthropogenic emissions alter atmospheric radiative balance. Altered balance shifts climate. Climate influences biosphere and cryosphere. Feedbacks amplify or dampen change. These processes obey the same thermodynamic and radiative principles governing Venus's greenhouse or early Earth's faint sun compensation. Only takes radiative forcing equations balancing incoming and outgoing flux. Only takes albedo changes, modifying absorption. Only takes carbon cycle perturbations, shifting equilibrium states. Awareness introduces agency. Agency introduces choice among pathways consistent with physical constraint. The laws do not prescribe outcomes. They delimit possibility space. Within that space, social systems, technologies, and values influence trajectories. Only takes collective coordination scaling beyond local interests. Only takes energy systems transitioning toward lower net emissions. Only takes resilience planning aligned with ecological limits. The broader cosmic arc remains indifferent to such choices, yet local consequences are profound. Even if Earth ultimately becomes uninhabitable under solar evolution, the interval before that transition spans roughly 1 billion years vast compared to human history. Preservation of biospheric complexity across even a small fraction of that interval depends on decisions measured in decades. Only takes understanding translating into policy. Only takes policy sustained across electoral cycles. Only takes feedback between science and governance remaining intact. Beyond Earth exploration extends continuity outward. Robotic probes traverse the solar system, analyzing planetary atmospheres, icy moons, and asteroid composition. Telescopes catalog exoplanets and map cosmic background radiation. Each mission refines context. Earth is neither central nor unique in structure, yet it remains singular in confirmed life. Only takes spectrometers identifying water vapor on distant worlds. Only takes landers sampling subsurface ice. Only takes data transmission across millions of kilometers. Whether life elsewhere mirrors terrestrial biochemistry or diverges fundamentally remains unknown. Carbon's versatility makes it likely elsewhere, yet silicon-based speculation persists in fiction more than laboratory feasibility. Extremophiles on Earth expand the envelope of plausible habitability, tolerating high radiation, acidity, salinity, and temperature. Only takes enzymatic adaptation stabilizing proteins under stress. Only takes membrane composition adjusting fluidity. Only takes genetic variation exploring biochemical parameter space. In contemplating ultimate fate, heat, death, proton decay, black hole evaporation, the scale dwarfs immediate relevance. Yet inclusion of these epochs completes continuity. A universe beginning in hot, dense expansion, structuring through gravity and cooling, will not reverse spontaneously absent new physics. Entropy's gradient defines direction. Only takes statistical mechanics linking microstates to macrostates. Only takes overwhelmingly probable configurations dominating long-term behavior. Only takes no evidence of global entropy decrease across isolated systems. The narrative thus resolves not into finality, but into asymptote. Complexity peaks locally and temporarily where energy flows permit. It fades when gradients dissipate. Earth's biosphere exemplifies such a peak, sustained by solar flux and geochemical cycling. Human cognition exemplifies a further emergent layer capable of modeling the peak's origin and forecasting its decline. Only takes nested hierarchies of structure. Only takes feedback loops linking scales from molecular to planetary. Only takes continuity of law across those scales. If a single principle underlies the entire account, it is transformation constrained by invariance. Matter changes state. Energy changes form. Structures assemble and disassemble. Yet conservation laws persist. The iron in planetary cores, the carbon in organic molecules, the photons streaming from stars, all participate in exchanges without vanishing from the ledger of mass energy. Only takes Noether's theorem linking symmetry to conservation. Only takes spacetime invariance implying energy conservation locally. Only takes empirical validation reinforcing theoretical symmetry. Thus, the closing perspective does not introduce new forces or exceptions. It returns to the beginning, a fluctuation in a quantum field within an expanding spacetime seed structure. Gravity amplifies that structure into stars. Stars synthesize elements. Planets condense. Oceans gather. Chemistry replicates. Life evolves. Intelligence reflects. Technology alters environment. Stars age. Galaxies merge. Black holes evaporate. Radiation thins. The chain contains no breaks in law, only transitions in state. Only takes continuity across 13.8 billion years and counting. Only takes equations tested in laboratories, describing events billions of light years away. Only takes recognition that origin and destiny are phases within one unbroken physical process. And in that process, for a fleeting yet measurable interval, the universe becomes aware of itself through organized matter on a small planet orbiting an ordinary star. That awareness neither halts expansion nor prevents entropy's rise, but it renders the continuum intelligible, tracing from first light to final fade, without invoking discontinuity. Only takes matter, energy, space-time, and time. Everything else follows. If everything follows from matter, energy, space-time, and time, then the remaining inquiry concerns scale of meaning within scale of law. Physical description accounts for transformation, yet description does not diminish consequence within local frames. The emergence of reflective systems introduces valuation intention projection phenomena grounded in neurobiology, yet experienced as purpose. These experiences do not suspend thermodynamics. They arise because thermodynamic gradients once permitted self-organizing chemistry to elaborate into cognition. Only takes electrochemical signaling across synapses. Only takes pattern recognition encoded in neural assemblies. Only takes memory stabilizing through protein synthesis and structural change. From that substrate comes narrative, and from narrative comes continuity extended psychologically beyond individual lifespan. Culture accumulates information, not genetically encoded, transmitting knowledge through language, symbol, and record. Writing externalizes memory. Digital storage multiplies its reach. The atoms forming storage media obey quantum mechanics as surely as those in stellar cores, yet arranged in patterns representing mathematics, law, art, and cosmology. Only takes binary states stabilized against thermal noise. Only takes error-correcting codes mitigating entropy locally. Only takes institutions preserving archives across generations. This cultural continuity modifies evolutionary dynamics. Biological evolution operates through differential reproduction over generations. Cultural evolution can occur within a single lifetime. Technological change accelerates feedback between knowledge and environment. Energy capture increases dramatically with fossil fuels, nuclear fission, and potential fusion. Each method converts mass or chemical potential into usable work bounded by efficiency constraints, derived from thermodynamic cycles. Only takes combustion oxidizing hydrocarbons formed from ancient photosynthesis. Only takes neutron capture inducing a fission in heavy nuclei. Only takes plasma confinement sustaining fusion reactions at extreme temperatures. With expanded energy access comes expanded planetary influence. Industrialization alters atmospheric composition, land cover, hydrological systems, and biogeochemical fluxes. Satellite measurements quantify ice mass loss, sea level rise, and atmospheric trace gas concentrations. These observations are not abstractions. They are empirical indicators of system response to forcing. Only takes radiometers measuring outgoing long-wave radiation. Only takes gravimetric satellites detecting ice sheet mass change. Only takes isotopic analysis distinguishing fossil carbon from biogenic flux. The recognition that human activity constitutes a geophysical force suggests a transitional epoch in Earth history. Whether labeled formally or informally, the shift underscores that local agency can influence global state. Yet the scale remains planetary, not cosmic. Stellar evolution will proceed independent of atmospheric policy. Galactic merger will ignore terrestrial debates. Only takes proportional reasoning distinguishing scales. Only takes humility regarding sphere of influence. Only takes clarity that responsibility is local even if context is vast. Within planetary timescales, biodiversity represents accumulated evolutionary experimentation across hundreds of millions of years. Each species embodies a lineage tracing back through branching descent to common ancestry. Extinction removes unique genetic combinations unlikely to reappear identically. Fossil evidence documents 5 major mass extinctions prior to the present. Current extinction rates exceed background levels, though magnitude relative to past events continues to be quantified. Only takes habitat fragmentation reducing viable population sizes. Only takes climate shifts exceeding adaptive capacity. Only takes invasive species disrupting ecological networks. Ecological systems exhibit resilience within bounds. Feedback loops can stabilize or amplify disturbance. Coral reefs bleach when thermal thresholds are crossed. Forests shift biome under persistent drought. Permafrost thaw releases methane reinforcing warming. These interactions mirror earlier planetary feedbacks described in deep time differing primarily in rate. Only takes rate of change exceeding buffering capacity. Only takes threshold dynamics triggering nonlinear response. Only takes cumulative perturbation crossing tipping points. The capacity to anticipate such thresholds arises from modeling grounded in physical law. Climate models incorporate radiative transfer equations, fluid dynamics, and chemical kinetics. Uncertainty remains in cloud feedbacks, regional precipitation shifts, and socioeconomic pathways. Yet the fundamental greenhouse effect is experimentally verified. Only takes laboratory spectroscopy confirming absorption bands. Only takes conservation of energy constraining system response. Only takes iterative refinement reducing predictive spread. Beyond mitigation lies adaptation. Coastal infrastructure, agricultural systems, and public health networks adjust to shifting baselines. Engineering solutions from seawalls to drought-resistant crops extend resilience, but cannot eliminate physical constraint. Only takes design accounting for probabilistic extremes. Only takes resource allocation aligned with risk assessment. Only takes recognition that adaptation has limits under accelerating change. Looking outward again, the search for extraterrestrial biosignatures continues. Spectroscopic detection of oxygen, methane, or other disequilibrium gases in exoplanet atmospheres could indicate biological processes, though interpretation demands caution. Future observatories aim to resolve smaller planets around Sun-like stars, increasing sample size. Only takes improved coronagraphs or star shades blocking stellar glare. Only takes longer integration times accumulating photon counts. Only takes statistical frameworks distinguishing signal from noise. If life proves common continuity extends widely across cosmic geography. If rare, its presence becomes statistically precious, though physically explicable. Either outcome remains consistent with natural law. Only takes abiogenesis pathways operating under suitable conditions. Only takes contingency limiting frequency. Only takes data surpassing speculation. Meanwhile, fundamental physics continues probing extremes. Particle accelerators test standard model predictions. Detectors search for dark matter interactions. Cosmological surveys map large-scale structure. Discrepancies between predicted and observed values, such as tensions in Hubble constant measurements, may signal new physics or unrecognized systematics. Only takes precision cosmology narrowing uncertainty bars. Only takes independent methodologies cross-validating results. Only takes anomalies persisting beyond experimental error to motivate paradigm refinement. Across all scales from subatomic to cosmic explanatory frameworks, aim for coherence. Quantum field theory governs microscopic interactions. General relativity describes gravitation and space-time curvature. Their reconciliation remains incomplete, yet each succeeds within tested domains. The universe's history unfolds under these frameworks without observed violation. Only takes domain validity respected within extrapolation. Only takes caution where empirical reach ends. Only takes openness to revision should observation demand. Returning to the continuum traced from primordial expansion to eventual entropy maximization. One observes that meaning as experienced by conscious beings arises within but not outside physical law. Value systems, ethical reasoning, aesthetic appreciation all correspond to neural processes shaped by evolution and culture. Their subjective richness does not contradict their material basis. Only takes emergent properties arising from complex networks. Only takes hierarchical organization producing novel macroscopic behavior. Only takes no requirement for external intervention beyond established forces. Thus, the arc concludes not with metaphysical assertion, but with structural recognition. The same gravity that collapsed a molecular cloud guides galaxies. The same electromagnetism that binds electrons to nuclei shapes chemical bonds in living cells. The same thermodynamics that cools white dwarfs constrains biological metabolism. Continuity is not poetic metaphor but physical fact. Only takes invariance across scale. Only takes equations applying universally within measured limits. Only takes time sufficient for consequences to manifest. Earth remains for now within a narrow window where energy flux, atmospheric composition, and liquid water coexist to sustain complexity. That window will close in deep future epochs, yet its present duration permits reflection and action. Reflection traces origin. Action influences trajectory within bounded scope. Beyond that scope, stars evolve and space expands indifferent to terrestrial narrative. Only takes acceptance of scale without diminishing significance locally. Only takes comprehension that transient does not mean trivial. Only takes understanding that continuity binds beginning, middle, and end into one process. From quantum fluctuations to conscious deliberation, from stellar birth to cosmic fade, the universe exhibits transformation without rupture. Matter organizes, reorganizes, disperses. Energy flows, degrades, radiates. Space-time curves and expands. And within this lawful unfolding, brief islands of awareness arise, examine the continuum, and inscribe its outline in language before yielding again to the processes that formed them. Only takes matter, energy, space-time, and time. The rest is sequence. Sequence implies direction. Yet direction in physics emerges from asymmetry rather than intention. The arrow of time is not imposed from outside the universe. It arises from boundary conditions in which entropy was lower in the past than it will be in the future. The early universe, though hot and dense, was remarkably uniform, representing a state of low gravitational entropy. As expansion proceeded, matter clumped under gravity, forming stars and galaxies, increasing entropy overall while permitting local complexity. Only takes initial smoothness, measured in microwave background fluctuations. Only takes gravitational instability, amplifying slight overdensities. Only takes statistical mechanics, defining probability distributions over microstates. The asymmetry between past and future explains why memory records prior states, but not future ones. Why causes precede effects in macroscopic experience, and why heat flows from hot to cold. These phenomena are not separate principles, but manifestations of the same entropic gradient. Neural systems encode memory through physical changes, synaptic strength adjustments, protein synthesis processes that themselves dissipate energy. Only takes irreversible biochemical reactions. Only takes ATP hydrolysis driving cellular work. Only takes microstates vastly outnumbering ordered configurations. If entropy increase defines temporal orientation, then the ultimate flattening of gradients in the far future corresponds to temporal exhaustion in a thermodynamic sense. Without gradients, no work can be extracted. Without work, no organized process persists. Yet even in such dilute conditions, quantum fluctuations remain, though their capacity to generate large-scale structure diminishes. Only takes vacuum fluctuations permitted by uncertainty principles. Only takes insufficient density for gravitational collapse. Only takes temperature approaching uniformity across space. On intermediate scales, millions to billions of years from now, structure continues to arise and decay in localized pockets. Stars form in remaining gas clouds. Planetary systems assemble. Life may emerge anew under favorable circumstances. These events do not contradict long-term entropic increase, because they occur within open subsystems fed by external gradients. Only takes localized density enhancement within molecular clouds. Only takes angular momentum conservation shaping protoplanetary disks. Only takes radiative cooling allowing fragmentation into stellar masses. Within each new star system lies potential for repetition of earlier arcs, accretion, differentiation, chemistry, biology. No guarantee exists, only possibility bounded by conditions. If the universe is sufficiently vast, or if inflation generated multiple causally disconnected regions, such repetitions may already exist beyond observational reach. Only takes spatial extent exceeding current horizon. Only takes physical laws consistent across regions. Only takes stochastic processes sampling parameter space. The concept of recurrence emerges in theoretical discussions, such as Poincaré recurrence, which in finite systems implies eventual return arbitrarily close to prior states given sufficient time. Yet the observable universe may not constitute a finite closed system in the required sense. Cosmic expansion and horizon growth complicate naive recurrence arguments. Only takes phase space sufficiently bounded. Only takes time exceeding exponential scales. Only takes assumptions about total degrees of freedom that remain unverified. Thus, while poetic notions of cosmic repetition captivate imagination, empirical grounding remains limited. What is grounded is conservation within known interactions and expansion driven by dark energy. If dark energy remains constant, accelerated expansion ensures that distant regions become permanently inaccessible. If it evolves, future dynamics could differ. Only takes equation of state parameter measured with precision. Only takes deviations from -1 indicating dynamic field behavior. Only takes observational baselines extended over cosmic time. Within present cosmic epoch, complexity flourishes where stars still burn and heavy elements circulate. The periodic table forged across generations of stellar nucleosynthesis provides the chemical diversity enabling planets and organisms. Carbon's tetravalence, oxygen's electronegativity, silicon's lattice-forming capacity. These properties derive from quantum mechanical structure of atoms. Only takes Schrödinger equation solutions defining electron orbitals. Only takes Pauli exclusion principle structuring periodic trends. Only takes electromagnetic interaction scaling with charge. Chemistry, in turn, shapes geology and biology. Silicate minerals crystallize from cooling magma. Water dissolves ions and transports them across landscapes. Organic molecules self-assemble into membranes under appropriate conditions. The interplay of hydrophobic and hydrophilic interactions drives lipid bilayer formation, creating compartments essential for life. Only takes amphiphilic molecules in aqueous environment. Only takes temperature within stability range. Only takes concentration exceeding critical micelle threshold. From compartments arise metabolism and replication. Metabolic pathways such as glycolysis and oxidative phosphorylation harness energy gradients through enzyme-mediated reactions. Replication copies genetic material with high fidelity, yet occasional mutation enabling evolution. Only takes polymerases catalyzing nucleotide addition. Only takes proofreading reducing error rates below lethal thresholds. Only takes variation interacting with environmental selection. Evolution does not anticipate future states. It filters present variation against current conditions. Yet cumulative filtering produces systems capable of anticipation at cognitive levels. Brains model environment to predict outcomes enhancing survival. Predictive coding frameworks in neuroscience interpret perception as hypothesis testing, constrained by sensory input. Only takes neural circuits minimizing prediction error. Only takes feedback between cortex and sensory pathways. Only takes metabolic support sustaining high energy demand of neural tissue. Human societies extend predictive modeling outward through mathematics and simulation. Orbital mechanics predicts planetary positions centuries ahead. Stellar evolution models forecast solar expansion. Climate models estimate temperature response to greenhouse forcing. These predictions remain probabilistic, constrained by initial conditions and parameter uncertainty, yet rooted in tested law. Only takes differential equations integrating over time. Only takes boundary conditions specified accurately. Only takes computational capacity scaling with model complexity. With prediction comes foresight regarding limits. Resources on a finite planet are bounded. Ecological sinks saturate. Energy transitions require infrastructure and coordination. Recognition of limits does not impose fatalism. It informs optimization within constraints. Only takes systems analysis, identifying leverage points. Only takes feedback loops mapped across sectors. Only takes governance structures capable of long-term planning. The cosmic context neither trivializes nor magnifies human endeavor. It situates it. Against billions of years, centuries appear brief. Against individual lifespans, centuries appear vast. Scale is relational. Only takes reference frame specifying measurement. Only takes units chosen to render magnitude comprehensible. Only takes translation between logarithmic and linear intuition. Ultimately, the sequence from low entropy beginning toward high entropy equilibrium defines a thermodynamic narrative, yet within it lie innumerable sub-narratives: planetary formation, biological diversification, cultural development. Each sub-narrative follows from the same fundamental interactions. No separate ontology is required to explain life or thought beyond emergent complexity grounded in physics and chemistry. Only takes hierarchical organization producing new effective laws at higher scales. Only takes coarse graining allowing macroscopic regularities. Only takes recognition that emergence does not imply independence from substrate. As this extended account reaches its present terminus, nothing essential changes in the underlying process. Stars continue to fuse hydrogen. Tectonic plates continue to drift. Atmospheric molecules continue to absorb and emit radiation. Neurons continue to fire. The difference lies only in description, an arrangement of symbols encoding understanding accumulated across inquiry. Only takes ink on paper or electrons in silicon. Only takes language mapping concept to pattern. Only takes continuity between physical substrate and abstract representation. The universe proceeds regardless of description, yet description permits internal models aligning expectation with outcome. From the hot, dense origin to the cooling asymptote from quark confinement to galactic superclusters, from abiogenesis to reflective awareness, the chain remains intact. Only takes consistent law applied universally. Only takes time unfolding consequences. Only takes no breach in conservation, no interruption in causation. Sequence persists until gradients fade and structure dissolves into uniformity. Even then, dissolution follows law. There is no final chapter outside physics, only continuation toward equilibrium. Only takes matter, energy, space-time, and time again, and without exception. Everything else is configuration. Configuration changes, law persists. Gradients diminish, yet never reverse without cause. If equilibrium represents maximal entropy under given constraints, then any future departure from it would require fluctuation permitted by underlying quantum statistics. In finite systems, such fluctuations are inevitable given sufficient time, but their probability decreases exponentially with scale. Only takes Boltzmann distribution weighting microstates. Only takes energy barriers suppressing macroscopic deviation. Only takes timescales exceeding comprehension by factors of exponentials stacked upon exponentials. In cosmological context, the meaning of fluctuation depends on global structure. If spacetime expands forever under a cosmological constant horizon, volumes become effectively isolated thermodynamic systems. Each approaches thermal equilibrium characterized by de Sitter temperature minuscule yet non-zero. Only takes dark energy density remaining constant. Only takes event horizon defining causal boundary. Only takes quantum field modes stretched beyond contact. Within such a horizon, rare fluctuations could in principle assemble low-entropy structures momentarily, but statistical reasoning indicates overwhelmingly that smaller fluctuations are more probable than larger ones. Hence, a solitary, self-aware configuration, arising briefly from chaos, would be statistically favored over reconstitution of an entire low-entropy cosmos. Only takes combinatorics of microstate counts. Only takes entropy difference between configurations. Only takes assumption of equilibrium background. This line of reasoning reveals tension between naive fluctuation cosmology and observed large-scale order. Therefore, many cosmological models posit that the observable universe did not arise as a mere fluctuation within equilibrium, but from boundary conditions set by inflation or other mechanisms that establish low entropy at early times. Only takes scalar field dynamics driving rapid expansion. Only takes potential energy dominating over kinetic. Only takes reheating converting vacuum energy into particles. Inflation smooths, curvature dilutes relics and seeds, structure through quantum perturbations, stretched to astronomical scales. These perturbations imprint temperature anisotropies measurable in cosmic microwave background radiation. Only takes Planck scale fluctuations amplified macroscopically. Only takes acoustic oscillations in primordial plasma. Only takes recombination releasing photons to free stream across space. Observational consistency between predicted and measured anisotropy spectra strengthens confidence in inflationary framework, though details remain under refinement. Competing models explore cyclic cosmologies, bouncing universes, or modifications to general relativity. Only takes alternative stress-energy components altering early dynamics. Only takes quantum gravity effects avoiding singularity. Only takes mathematical consistency with observational constraints. Whether the universe began in an absolute sense or transitioned from prior phase remains unsettled, yet any viable account must reproduce thermodynamic arrow and large-scale homogeneity observed. The interplay between quantum theory and gravitation stands at frontier of understanding. General relativity treats spacetime as dynamic geometry responding to energy and momentum, while quantum field theory describes matter and forces within fixed background. Reconciling these frameworks requires quantizing geometry or deriving gravity as emergent phenomenon. Only takes Planck length-defining scale where classical description fails. Only takes uncertainty in metric fluctuations. Only takes renormalization procedures extended beyond established regimes. Approaches such as loop quantum gravity string theory and asymptotic safety pursue different strategies, each constrained by requirement of internal consistency and empirical viability. None yet yields decisive experimental confirmation, though theoretical progress refines mathematical coherence. At macroscopic scales, relativity continues to predict gravitational waves, black hole mergers, and time dilation with remarkable precision. Only takes interferometric detectors measuring strains smaller than proton diameter. Only takes orbital decay observed in binary pulsars. Only takes synchronization of atomic clocks across varying gravitational potentials. Black holes, once theoretical curiosities, now occupy central role in astrophysics. Their event horizons conceal singularities according to classical theory. Yet quantum considerations introduce Hawking radiation, implying gradual mass loss over immense durations. Only takes virtual particle pairs near horizon. Only takes one partner escaping to infinity. Only takes conservation of energy reducing black hole mass. For stellar mass black holes, evaporation time exceeds current age of universe by orders of magnitude. For supermassive black holes at galactic centers, it exceeds even those by further magnitudes. Eventually, however, if no new matter accretes and expansion continues, evaporation will proceed until only radiation remains. The information paradox, whether information about infalling matter is preserved, stimulates debate linking thermodynamics, quantum entanglement, and spacetime geometry. Holographic principles suggest information content scales with surface area rather than volume. Only takes entropy proportional to horizon area in Planck units. Only takes duality between gravitational and non-gravitational theories. Only takes consistency with unitarity of quantum mechanics. If holography holds universally, then description of any region may be encoded on lower dimensional boundary, challenging intuition about locality. Yet empirical predictions remain subtle and difficult to test. As cosmic time extends, stellar populations evolve. Main sequence stars exhaust hydrogen, expand into red giants, shed outer layers, and leave behind white dwarfs, neutron stars, or black holes, depending on mass. Only takes hydrostatic equilibrium balancing gravity and pressure. Only takes nuclear fusion rates determined by temperature and density. Only takes Chandrasekhar limit defining white dwarf stability. Galaxies gradually exhaust cold gas reservoirs, reducing new star formation. Interactions and mergers redistribute angular momentum and trigger episodic bursts, but long-term trend declines. On trillion-year timescales, star formation effectively ceases. Only takes gas consumption exceeding replenishment. Only takes cosmic expansion preventing fresh inflow. Only takes proton stability over relevant durations. If protons decay, as some grand unified theories predict, then even white dwarfs and neutron stars ultimately disintegrate into radiation and lighter particles. Only takes half-life finite though immense. Only takes baryon number violation permitted. Only takes observational constraints setting lower bounds beyond current measurement. Should protons prove stable, matter persists longer, but gravitational interactions gradually eject remnants from galaxies, leading to sparse distribution of compact objects orbiting nothing in particular. Dynamical relaxation redistributes energy until only tightly bound systems survive. Only takes 3 body encounters transferring kinetic energy. Only takes escape velocity exceeded by lighter components. Only takes cumulative perturbations over astronomical intervals. Thus, the far future trends toward dilution, punctuated by rare interactions. Throughout physical constants, shape possibility. Slight variation in fine structure, constant gravitational coupling, or particle masses would alter stellar lifetimes, chemical bonding, and nuclear stability. Anthropic reasoning observes that observers necessarily find themselves in parameter ranges, permitting complexity. Yet explanation for those ranges remains open question. Only takes multiverse hypotheses, distributing constants across domains. Only takes selection effect biasing observation. Only takes caution distinguishing explanatory from tautological reasoning. Regardless of ultimate explanation, within observed parameter, set complexity emerges and reflects upon itself. Reflection does not suspend thermodynamics. Cognition dissipates energy, culture transforms environment, technology reconfigures matter. Yet reflective systems can intentionally redirect energy flows, at least locally, and temporarily altering trajectories within bounds of law. Only takes feedback between knowledge and action. Only takes storage of information external to biological memory. Only takes cooperative structures scaling beyond individuals. The cumulative record of inquiry, astronomy, physics, chemistry, biology constitutes organized information resisting entropy locally by exporting it elsewhere. Libraries, databases, and instruments are low-entropy arrangements maintained through continuous energy input. If energy ceases, degradation follows. This is not pessimism but statement of condition. Only takes cessation of maintenance. Only takes thermal noise and chemical reaction. Only takes time. The cosmic narrative therefore contains no privileged endpoint accessible within finite duration. There is extension toward asymptotic states, not abrupt termination in ordinary models. Speculation about vacuum decay or phase transitions altering fundamental constants introduces possibility of sudden change, but such scenarios remain hypothetical pending evidence. Only takes metastable vacuum with lower energy state accessible. Only takes quantum tunneling probability non-zero. Only takes bubble nucleation expanding at near light speed. Should such event occur, local physics would transform irreversibly, yet prediction of timing remains impossible with current knowledge. Absent such discontinuity, continuation follows, established trajectory, expansion, cooling, dilution, occasional fluctuation, eventual approach to maximum entropy, consistent with cosmic horizon. The essential pattern remains from beginning to end: conservation, causation, statistical tendency. Only takes matter and energy interacting through invariant equations. Only takes space-time geometry responding accordingly. Only takes no exemption for scale or epoch. Configuration shifts from plasma to star to ash to radiation, yet substrate persists until perhaps even space-time itself reaches quantum-limited minimal structure. Whether anything meaningful can be said beyond that lies outside empirical reach. Within reach lies recognition that every present structure participates in larger thermodynamic arc. No special exemption applies to galaxies, organisms, or civilizations. Each forms persists through energy throughput and dissipates. The continuity of law across these transitions underwrites coherence of explanation. Only takes invariance under transformation. Only takes symmetry broken only by boundary conditions. Only takes relentless progression of probability favoring more numerous states. Thus, continuation proceeds not as narrative climax, but as statistical unfolding. Nothing required beyond initial conditions and governing equations. Nothing permitted outside them. Only takes time, and time continues until gradients are spent. Gradients thin, yet do not vanish instantaneously. Asymptotes are approached, not crossed. In an expanding universe dominated by dark energy, matter becomes increasingly isolated as co-moving distances stretch beyond causal contact. Galaxies not gravitationally bound to local groups recede past event horizons, their light redshifted into undetectability. Only takes metric expansion scaling with exponential factor. Only takes wavelength stretching proportional to scale factor. Only takes finite sensitivity of detectors. From within any gravitationally bound remnant, such as a future merged system of present galaxies, cosmic history, beyond that island, gradually fades from observable record. Background radiation cools photons, dilute relic neutrinos, thin into near irrelevance. Only takes temperature inversely proportional to scale factor. Only takes particle number density decreasing with volume. Only takes no new high-energy injection. Astronomers of that epoch, if any observers remain, would infer a cosmos limited to their bound structure, unless they retained inherited knowledge encoded from earlier eras. The epistemic horizon thus mirrors the physical horizon. Knowledge requires signal. Signal requires interaction. Interaction requires causal contact. As contact disappears, so too does empirical access. Yet law does not change with ignorance. Gravitation continues to govern orbital motion. Quantum electrodynamics continues to regulate atomic spectra. Nuclear forces continue to bind residual nuclei. Only takes invariance of coupling constants. Only takes conservation principles unviolated. Only takes absence of phase transition altering symmetry group. Within gravitationally bound remnants, long-term dynamics proceed through relaxation and decay. Stellar remnants, white dwarfs, neutron stars, black holes interact through rare encounters. Over quadrillions of years, gravitational perturbations eject many objects into intergalactic darkness. Only takes cumulative small-angle scattering. Only takes equipartition tendency distributing kinetic energy. Only takes escape velocity surpassed by lighter bodies. White dwarfs cool toward black dwarfs, radiating away residual thermal energy until reaching equilibrium with ambient background itself, approaching de Sitter temperature. Neutron stars cool more rapidly initially, then persist as degenerate spheres, sustained by neutron degeneracy pressure. Black holes dominate mass budget of surviving bound systems due to merger history and mass concentration. Their slow Hawking evaporation becomes relevant only after unimaginable spans, yet inevitability follows from semi-classical analysis. Only takes horizon temperature inversely proportional to mass. Only takes emission power scaling with inverse square of mass. Only takes no external accretion replenishing loss. When evaporation time arrives, black holes radiate away mass energy into photons and lighter particles, further homogenizing energy distribution. If proton decay occurs, baryonic matter disintegrates earlier, transforming solids into radiation and leptons. If not, gravitational capture by black holes may eventually incorporate most baryons prior to evaporation epoch. The sequence depends on microphysical parameters not yet empirically fixed. Only takes grand unification scale determining decay probability. Only takes stability of lightest baryon ensured or broken. Only takes observational patience exceeding current limits. Throughout these epochs, quantum fluctuations persist as irreducible feature of fields. Vacuum energy, if constant, defines de Sitter horizon with associated entropy proportional to horizon area. This entropy represents maximum information content accessible within that causal patch. Only takes Bekenstein-Hawking relation linking entropy and area. Only takes Planck units establishing proportionality. Only takes holographic bound constraining degrees of freedom. As expansion proceeds, horizon area asymptotically approaches constant value determined by cosmological constant implying finite entropy bound per observer. Finite entropy implies finite number of distinguishable states within patch, which in turn implies eventual recurrence over inconceivably vast timescales if dynamics remain unitary. Only takes Hilbert space dimension finite. Only takes evolution operator preserving norm. Only takes time exceeding recurrence interval exponential in entropy. Such recurrence times dwarf even black hole evaporation scales, rendering practical recurrence irrelevant to any transient structure. Yet in principle, statistical return remains encoded in formalism. Whether this reasoning applies depends on unresolved questions about quantum gravity and global structure. Still, the implication is that asymptotic emptiness does not equate to metaphysical nothingness, but to maximal entropy state under constraints. No external reset intervenes. Only fluctuation permitted by law. The concept of heat death therefore denotes thermodynamic equilibrium, not annihilation of existence. Energy remains, difference diminishes. Without gradients, no engine operates. Without free energy, no computation proceeds. Without computation, no memory accumulates. Information requires physical medium with distinguishable states maintained against noise. In equilibrium, noise dominates. Distinctions blur. Only takes temperature uniformity across region. Only takes no reservoir colder than system. Only takes inability to export entropy elsewhere. Consequently, any structure capable of sustained complexity must arise during epochs where gradients are abundant. This condition characterized early and middle cosmic eras, not terminal ones. The rarity of low entropy beginnings therefore underlies all subsequent richness. Why such beginning occurred remains open. Some proposals invoke inflationary attractors making smooth initial conditions probable. Others appeal to deeper principles not yet articulated. Only takes boundary condition selecting specific microstate distribution. Only takes measure over solution space defined. Only takes theoretical framework capable of empirical test. Until such account achieves confirmation, low entropy origin stands as empirical fact without final explanation. From that fact flows arrow of time structure formation chemistry life cognition and reflection. The continuity between primordial plasma and present thought is uninterrupted chain of causation. No insertion of external agency required, no suspension of conservation observed. Complexity arises because local decreases in entropy are compensated by greater increases elsewhere consistent with second law. Only takes open systems exchanging energy and matter. Only takes radiative flux from hot star to cooler space. Only takes planetary surface far from equilibrium. On planetary scales, tectonics recycle carbon magnetic fields, shield atmospheres, orbital stability, maintains climate within ranges permitting liquid solvents. Each factor depends on mass composition and formation history, rooted in stellar evolution. Only takes supernovae enriching interstellar medium with heavy elements. Only takes angular momentum distribution setting planetary spacing. Only takes stochastic impacts altering trajectories, yet within gravitational framework. Civilizations, should they arise, manipulate energy flows through technology extending influence beyond immediate biological constraints. Harnessing fossil fuels, nuclear reactions, or stellar radiation modifies planetary entropy budgets, but cannot escape thermodynamic accounting. Only takes efficiency less than unity. Only takes waste heat dissipated. Only takes resource depletion unless replenished. Long-term survival of complex systems demands adaptation to changing cosmic environment, stellar brightening, orbital shifts, eventual stellar death. Hypothetical strategies include migration, artificial habitats, or energy harvesting from black hole accretion. Feasibility depends on physics, not aspiration alone. Even maximal engineering cannot negate universal expansion or final equilibration under cosmological constant if that constant persists. Only takes speed of light limiting travel. Only takes accelerating metric separating regions faster than signal propagation. Only takes finite accessible mass energy within horizon. Thus, limits are structural, not merely technological. Recognition of structural limits does not diminish significance of transient achievements. Rather, it situates them within finite window of opportunity defined by cosmic evolution. Every act of construction, discovery, or communication occupies interval between initial low entropy and eventual equilibrium. The window is vast relative to human timescales, yet finite relative to cosmological infinity. This finitude grants direction without invoking purpose. Direction arises from gradient, gradient from boundary, boundary from initial condition. Remove low entropy boundary and arrow dissolves. Retain it and processes unfold inexorably. Only takes mathematics expressing dynamical law. Only takes initial data specified on space-like surface. Only takes integration forward yielding unique evolution under deterministic equations or probabilistic evolution under quantum rules. Determinism at fundamental level may coexist with effective unpredictability due to chaos or quantum indeterminacy. Unpredictability does not imply absence of law. Sensitivity to initial conditions amplifies minute differences into macroscopic divergence, yet evolution remains governed by same equations. Only takes nonlinear coupling among variables. Only takes finite precision in measurement. Only takes exponential divergence quantified by Lyapunov exponents. Hence, future states are constrained though not fully predictable in practice. The overarching trajectory expansion cooling entropy increase remains robust across microstate variations. This robustness explains why cosmology can project far future trends despite uncertainty in detail. When gradients thin to near uniformity, physical description simplifies dilute radiation in exponentially expanding spacetime with isolated evaporating remnants. No dramatic finale, only gradual attenuation. Eventually, even photons redshift toward arbitrarily low energies approaching horizon temperature floor. Only takes exponential scale factor growth. Only takes photon energy inversely proportional to wavelength. Only takes no mechanism to reconcentrate energy globally. If cosmological constant truly constant, this state endures indefinitely modulo rare fluctuations. If constant decays or transitions, new phase could begin, but such speculation remains beyond verified data. Therefore, continuation consists of diminishing interaction, density lengthening times between events, and approach to thermodynamic stasis. From quark-gluon plasma to cold diffuse radiation arc spans extreme contrasts, yet obeys single framework. Nothing extraneous required, nothing exempt from accounting. Only takes fields, particles, space-time geometry, and statistical law. Configuration after configuration arises and dissolves each contingent on prior state, none violating overarching principles. The narrative does not culminate in exception. It attenuates into equilibrium. Only takes time sufficient for probabilities to assert dominance over structure. Time extends, gradients fade, law persists. As equilibrium approaches within each causal domain, description shifts from dynamics rich in structure to dynamics sparse in interaction. Yet even sparsity is a configuration of fields rather than absence. The metric continues to expand under influence of dark energy. Quantum fields remain defined at every point. Vacuum expectation values persist. Only takes cosmological constant or equivalent stress energy maintaining acceleration. Only takes field operators defined on curved spacetime. Only takes persistence of commutation relations, irrespective of temperature. In near-empty de Sitter space, particle horizons define finite regions with associated entropy and temperature. This temperature, though extraordinarily low, implies non-zero rate of thermal fluctuation. Fluctuation amplitude scales with Boltzmann suppression, rendering macroscopic deviations fantastically improbable, but not forbidden. Only takes exponential factor e to the power of minus delta E over T. Only takes energy gap large relative to horizon temperature. Only takes timescale proportional to inverse probability. On such scales, language such as future loses intuitive meaning. Intervals exceed any conceivable biological or technological duration. Yet mathematical formalism remains indifferent to intuition. If Hilbert's space of a horizon patch is finite dimensional recurrence, theorems imply that system will, after times doubly exponential in entropy, revisit states arbitrarily close to earlier ones. Only takes unitarity preserving information. Only takes bounded energy spectrum. Only takes finiteness of accessible states. Whether quantum gravity ultimately enforces such finiteness remains debated, but semi-classical reasoning suggests entropy proportional to horizon area in Planck units, thus finite for constant dark energy. If so, recurrence is property of closed patch, though inaccessible in practice. The recurrence would not restore global early universe conditions, only reproduce configurations within that finite domain. No violation of second law occurs, because recurrence time vastly exceeds relaxation time. Entropy fluctuates downward only as rare statistical event consistent with overall equilibrium ensemble. Only takes distinction between ensemble average and specific trajectory. Only takes microscopic reversibility underlying macroscopic irreversibility. Only takes boundary condition selecting low entropy initial macrostate. The question of why boundary condition was low entropy rather than typical equilibrium state remains central. Some proposals invoke cosmological naturalness principles. Others suggest that inflation generically produces large, smooth regions from broader initial conditions. Yet inflation itself requires suitable preconditions for onset, including sufficiently homogeneous patch dominated by potential energy of scalar field. Only takes slow roll conditions satisfied. Only takes potential flatness within parameter range. Only takes quantum fluctuations not disrupting coherence prematurely. Attempts to embed inflation within broader theory such as string landscape introduce multiplicity of vacuum states with varying constants. In that context, eternal inflation may generate vast ensemble of bubble universes sampling parameter space. Only takes false vacuum decay nucleating bubbles. Only takes expansion rate of inflating background exceeding bubble collision rate. Only takes anthropic selection limiting observed parameters to life-permitting subset. Such frameworks shift explanatory burden from unique initial condition to statistical distribution over many regions. Empirical access to other regions remains absent. Predictions must derive from statistical correlations within our observable patch. Debate persists regarding measure problem and testability. Nonetheless, regardless of multiverse or single universe interpretation, thermodynamic arrow within each region arises from its own low entropy boundary. Without that boundary, no sustained complexity forms. Complexity thus remains contingent on cosmological history. Within the remaining stellar lifetimes of our local gravitationally bound system, possibilities for organized activity depend on resource management and adaptation to changing luminosity. The sun's gradual brightening over billions of years alters habitable zones. Planetary climates respond through feedback among atmosphere, ocean, and geology. Only takes stellar evolution increasing core temperature as hydrogen depletes. Only takes carbonate-silicate cycle regulating carbon dioxide concentration. Only takes tipping points beyond which regulation fails. On longer scales, post-main sequence expansion transforms inner planets, potentially engulfing or sterilizing them. Hypothetical advanced systems might migrate outward or construct artificial habitats powered by stellar output. Engineering feasibility constrained by material strength, energy efficiency, and orbital mechanics. Only takes conservation of angular momentum governing relocation. Only takes thermodynamic cost of large-scale construction. Only takes radiation shielding against intensified flux. After stellar death, residual energy sources diminish. White dwarf cooling offers limited gradient. Gravitational interactions among remnants provide sporadic energy release. Extraction of rotational energy from black holes via processes analogous to Penrose mechanism could extend usable energy interval. Only takes ergosphere around rotating black hole. Only takes magnetic fields coupling plasma to rotation. Only takes efficiency below unity, yet non-zero. Eventually, however, as black holes evaporate and matter disperses, available free energy declines irreversibly. No mechanism within standard physics reestablishes global low-entropy condition. Thus, window for sustained computation or life is finite even if exceedingly long. Recognition of finitude reframes significance of present era. It resides within early fraction of stelliferous epoch, when star formation remains active and heavy elements abundant. From nucleosynthesis in first generations of stars to complex chemistry on planetary surfaces, chain of causation spans cosmic expansion history. Only takes triple alpha process forming carbon. Only takes supernova shock waves dispersing elements. Only takes molecular clouds cooling to collapse anew. The same gravitational instability that seeded galaxies continues to operate locally, though diminishing as gas depletes. Over trillions of years, star formation rate asymptotically approaches zero. Statistical description transitions from active galaxy population to relic-dominated cosmos. Yet through all transitions, equations of motion remain invariant. Constants measured today appear unchanged over observable history within experimental precision. Spectroscopic observations of distant quasars constrain variation in fine structure constant. Pulsar timing constrains gravitational dynamics. Laboratory experiments test charge conservation and Lorentz invariance. Only takes comparison across redshift baselines. Only takes precision metrology of atomic transitions. Only takes absence of detected drift within uncertainties. Stability of law across space and time underwrites extrapolation into far future. If constants were to vary dramatically, observational traces would likely already appear. While absolute certainty, unattainable cumulative evidence favors persistence. Therefore, projection of continued expansion and entropy increase rests on empirical foundation rather than speculation alone. Even quantum indeterminacy does not undermine large-scale thermodynamic direction because probabilities aggregate overwhelmingly toward more numerous microstates. Only takes combinatorial dominance of disordered configurations. Only takes decoherence suppressing macroscopic superpositions. Only takes coarse graining defining entropy macroscopically. In final accounting, cosmic future contains no abrupt metaphysical rupture within established models. It is extension of same processes operating since earliest measurable epoch field interactions, space-time dynamics, statistical evolution. Structures arise where gradients permit. Structures fade where gradients exhaust. Between origin and asymptote lies finite interval rich in transformation. After asymptote lies equilibrium, punctuated by fluctuation, so rare as to render narrative nearly static. Only takes patience measured not in centuries, but in exponentials of entropy. If recurrence occurs, it does so without memory of prior cycle, except insofar as identical configuration reappears as consequence of unitary evolution. There is no external archivist preserving continuity beyond physical state itself. Information is physical. Preservation demands substrate. Substrate obeys entropy constraints. As gradients vanish, so too does capacity for long-term record. The arc from quark confinement to reflective analysis, from plasma opacity to transparent cosmos, from dense uniformity to structured complexity, and onward to dilution, requires no supplementary principle beyond those already articulated by physics. Only takes initial low entropy invariant law and sufficient time. With those ingredients, galaxies condense stars, ignite planets, coalesce, chemistry organizes, cognition reflects, and eventually radiation thins into near featurelessness. The process is not guided toward endpoint. It unfolds according to differential equations and probabilistic rules. Meaning, if a sign arises within subsystems capable of representation, not within equations themselves, equations remain indifferent. They describe curvature responding to energy amplitudes evolving in Hilbert space distributions, shifting toward equilibrium. Only takes consistency across scale. Only takes no exception granted to complexity. Thus, continuation proceeds until no further free energy remains within horizon, at which stage physical description simplifies to near-static geometry with minimal excitations. Even then, quantum fields fluctuate. Even then, mathematical structure endures as long as spacetime endures. Whether spacetime itself is emergent and subject to deeper transition remains open research question. Yet any deeper layer must reproduce observed thermodynamic arrow and large-scale behavior within its domain of validity. Until evidence dictates, revision extrapolation follows current framework. Time extends, entropy increases, structure forms and dissolves, law persists. Nothing more is required, and nothing less suffices.